Hey everyone and welcome back to PrepFusion. Today we'll start about CRO. We'll study about CRO. So CRO is an important topic for measurements chapter. So around 1 marks can come. 1 marks can come generally. They ask one question at least from CRO every alternate year. Okay, that's the trend. They cannot ask as well. They can ask as well. Okay, it depends. So it's an important topic. So we'll study this. So I will teach you in such a manner that obviously the things that are written in book, that is fine. All those things are fine. But what are actually not written in book, which things you get confused. So that is the main purpose of me teaching you. So CRO is this particular device which has a lot of things. Like first of all, this, right? We have an electron gun assembly. Then this electron gun is gone through two types of plates. One is vertical plate, then horizontal plate, and then finally this is the phosphor screen where we actually observe the output of the CRO. Okay, so a few things I wanted to explain is the one thing. I know you have already studied CRO in your colleges or basic things you know about CRO. Okay, main thing is what we want. What is our aim? Aim is to show the output voltage, to show the waveform, plot the waveform on the screen. So our main purpose or aim is, what is the aim? Don't forget the aim. Aim is to plot, just hold on, to plot output voltage waveform, okay, on screen. Now how do we achieve this? So what we do is, we have a, I will just give you a quick summary, okay, a brief overview. Basically, I have a screen over here, and when some electron at very high speed collides with the screen, right, it produces a luminance. Luminance means light. Okay, whichever is producing light, you're seeing light, right? It produces a light on the screen. The point at which it collides with the screen, it produces a light, luminance. Okay, and that light is observed by us. So what we do is basically move the electron almost similar to the waveform, just like how the waveform is there, right? Let's say some waveform is there, right? Waveform is there. This is y with respect to some x, okay, or some time, and this is sinusoidal. So what the CRO does is it exactly mimics this waveform. How it mimics? It basically moves the electrons. If at t equals to 0, the electron will be at 0 position. At t equals to some 0.01 or 0.1 second, it will be some positive position. So we are here, I have the electrons, and what I am doing is I am moving the electrons. And as soon as I move the electrons, and those electrons are actually then blasted onto the screen at that particular position. And once they blast onto the screen, right, they are collide onto the screen, it provides a luminance. And that luminance is seen by us with respect to the, as the waveform. We see the waveform. If you have ever observed a CRO, you will see some waveforms like that. So it is continuous, right? It is continuous with respect to time. Okay, it is not like it is stationary. It is, electrons are constantly coming in and moving. So basically what we do is, we have an electron generator that generates electron, then fires electrons, okay? And this vertical and horizontal plates are just there to mimic the voltage waveform, mimic the output or the input waveform which we want to actually display on the screen, okay? And as it mimics it, then it positions the electrons according to the input waveform that you want to mimic, and then it collides with the screen, and as soon as it collides, we get a luminance. So that is the basic purpose, right? That is the main purpose of the waveforms basically. So here few things are given here, theoretical. You can read this. I will just read this very quickly. I go through this, but this is already in the book, and this will be in the notes as well. You can go through this. Basically, cathode ray oscilloscope is essentially a laboratory instrument used for visualizing and analyzing the waveform. So that, as I told, right, it is mainly used for visualizing the waveforms, primarily through displaying voltage signals as they vary over time. The CRO allows the study of time-dependent electrical signals, providing a visual representation of an input waveform. While CROs inherently work with voltage signals, they can be adapted to measure the other physical quantities such as displacement, strain, acceleration, and pressure by using transducers. Okay, so we can use this. Unlike digital meters that display a single value at a time, it can only like digital meters, if you know, we'll study digital meters as well after this lecture. They only display a single value at a time. They cannot totally display like a waveform. They cannot display plot. They can only display a single waveform at a time. They can display RMS. They can display average. They can do those computations, but they cannot display the waveform actually. If you want to see the waveform, they cannot do that, digital meters. But CRO shows real-time waveforms, enabling both dynamic and comparative analysis by signals. The versatility of CRO makes it invaluable for measuring parameters such as peak-to-peak voltage, root mean square, R frequency, and phase difference. All these things we'll study how to measure all these things. Okay, and that's why CRO is so old. Still, we use it in our electrical laboratories because it is so versatile and dynamic. Okay, so basic thing I have already explained, that I have electron gun that we fire. And then I have two plates. One is the vertical deflection plate and is the horizontal deflection plate. So what does vertical deflection plate and horizontal deflection plate means? So in the vertical deflection plate, right, what do I give input? So how can I deflect the electrons? So electron is here, right? Electron is here. My electron has reached here. Electron has reached here. It is inside these plates. There are two ways I can deflect the electrons, because there are two ways of forces. One is the magnetic force, that is FV, that we have studied. Like if you haven't already studied electrostats and magnetostats from me, please go on our YouTube channel. It's fully present. Okay, on our YouTube channel you can completely study electrostat and magnetostat for free. Okay, so there can be two types of forces. One is electric field force, another is magnetic field force. Which one shall I choose? I know actually this magnetic field, right, it always acts in the perpendicular direction to the electron. So it can actually never move the electron. It can actually only what can do? It can change the direction, but it cannot accelerate, or it can never force the electron to go in a particular direction. It cannot do that. Magnetic field force cannot do that, but electric field can do that. So I will choose electric field. How to generate electric field? Parallel capacitor. So this is just like a capacitor, right? There are two plates which generates electric field. Okay, so we generate electric field in this vertical and the horizontal electric field, horizontal deflecting plates. Electric field is generated here. So as we generate the electric field, what will happen is that once this electric field reaches here, the electric field can move in this top and bottom direction. If the force is positive, let's say with respect to this, right, this is plus, this is minus. So electric field will be in this direction. This is the direction of the electric field. Then electrons will move in the opposite direction, because electron has opposite charge. Okay, electrons has opposite charge. So electrons will be attracted towards positive. If it is negative, that's plus minus, so electrons will be going downwards. So what I am doing, I am controlling the movement of the one direction, that is top and bottom. And what is top and bottom? It is the vertical direction. So what I am doing is, I am controlling the movement. This is X and this is Y. I'm just controlling the movement of this top and bottom direction. So I'm controlling the movement of vertical direction. That's why the name vertical deflection plate. That is the reason it has a name as vertical deflection plate. Okay. And where does this input it gets from? It gets the input from this input signal. Okay. And a vertical amplifier is there to obviously amplify the signal. And few other things are there, block diagrams. We don't need to go over that. Main concept you need to understand is we give the input here. Okay. And the electric field in the vertical plate, right, EV, is a function of the input signal of Y. So obviously as EV will change, the force on the electrons will change, electrons will move, so the movement in the y-axis will change. But there is a problem here. What is the problem? I can only change the movement in this direction, right, in this top and bottom. But can my electrons move in this direction? No, it cannot move in this direction. Due to that reason, I have another plate known as horizontal deflection plate. So because I need to move my electron, like I need to accelerate my electron in the x direction as well, right? Because I want to plot with respect to time. Correct? I want to plot with respect to time. So I will write here x only. This will be equals to time. So to move the electron on the x direction, I need another plate known as horizontal deflection. As it is horizontal movement, that's why the name horizontal deflection. Now generally, there are two ways to go about it. First of all, we'll study about waveforms, plotting waveforms with respect to time. Then I will plot waveforms with respect to them. That I will come to later. But first of all, I will tell you the concept plotting waveforms with respect to time. So what we do is we have a time-based generator. So in the horizontal plate, right, we don't give directly from the input signal. We have a time-based generator which then gets amplified and then that is given to the input. So what we do is we just constantly move the electron from left to right. So this electron is, let's say, on this end, it will move from this end to this end, right? Again, it will come back here, then again it has to move there. That I will come to how it does that. That I will come to, don't worry. But the basic thing is it is here and it will go on the right hand side. So let's say it is totally on like this. I will just draw the 3D figure of this. Okay. My electron is here and it will totally go here, right? So from here to here, what type of signal should I give? What type of signal should I give? So if I observe that I need to give like a ramp signal. Why? Because I know my time is constantly increasing, right? My time is always positive increasing in a straight fashion. So x equals to t. What is x equals to t? So here the input to the x, right, is simply t. So it is like a linear function, right? So I will give a ramp like function to the horizontal plates. So if I provide a ramp like function to the horizontal plates, basically what will happen, the electrons have the freedom to move in this direction as well. So it will, I cannot, like in a time domain waveform, right? Do I ever go back? I don't ever go back, right? It continuously increases. So obviously I will not go on the left hand side, I will only go on the right hand side. So I have the provision to go on this. So according to the like point on the y axis and the point on the x axis, some electron will be here, then some electron will be here, then some electron will be here, like that it will plot, right? So it is just, what are these? These are just crashing here, right? These are just colliding at the phosphor screen, and I am getting a luminance. So this is the luminance of it. So the time difference between these two electrons, right, consecutive collisions, is so less that you won't be able to see that they are actually discrete. Okay, it is actually, you will feel that it is totally continuous, but actually it is discrete. But there are so many electrons, and the time difference between those two hitting the screen is so less that it will be actually almost continuous. In your eyes won't be able to detect that change. Okay, it will be continuous. So that is the main working principle of CRO. Okay, that's it. Because you have understood the CRO. That's it, right? Other things are there to obviously help and make the circuit bigger, make it more efficient. All those things are there obviously, but main concept, right? Main concept, I think you have understood. That is the main aim of what we want to do. Okay, so because I know this is not written in the book. This is not written in the book. This is not anywhere. You have to understand this. Okay, by your own analysis. So yeah, these are the few things that I wanted to talk about. Amplifiers are there. Now let's talk about like a few like in depth about this vertical deflection and horizontal deflection. So vertical deflection plates P1 and P2 are parallel to each other. In the absence of any voltage, the electron beams strikes the point O. If I don't have any electrons, right, I will fire the electrons here, and there is no force between these two. It will directly touch the center of the screen. Oh, okay. I will just see a point. If you don't have any, if you haven't given any input, right, you will see the CRO has just a point there. Okay, it's just a point. But what does the horizontal deflection do? Alternating voltage applied to the horizontal deflection plate causes the electron plate to move horizontally. That's why the name horizontal deflection plate. The beam can be deflected from x1 to x2. So from x1 from the left to right, and this is from y1 to y2, from below to top. Along the horizontal axis based on the polarity of the voltage, the deflection of the electric beam is directly proportional to the voltage applied to the deflecting beams. This enables precise control. So we know in a capacitor, right, if you remember, VD was proportional to E into D, right? VD was proportional to into E. Basically, it was VD was equals to E times D. So it's pretty simple, not that difficult. So that's why it is directly proportional. I will apply the input voltage here, and it will be proportional to the electric field, and the force on the electron is directly proportional to the electric field, right? So obviously, in turn I can say force is directly proportional to the voltage, applied voltage. So like that, the relationship follows. Okay. Yeah, so if I trace the two waveforms, right, together, what will happen? So this is my y-axis and this is my x-axis basically. So here in the y-axis, I'm giving the input. So input, let's assume it has a sinusoidal signal. Okay, so if I give an input signal, so my y value of this screen, right, will be fixed. This is A. Y value from the distance from the horizontal axis, the distance will be fixed. But what about the distance from this vertical axis? That will be given by the ramp. So there will be a ramp, and that will be a sawtooth light function. Why that will be a sawtooth light function, I will just explain in a second. Okay, so the distance of air from this horizontal vertical axis is somewhere here, right? So A will be somewhere here with respect to the vertical axis, and with respect to the horizontal axis, it will be somewhere here. So in the screen, I will see this point. Then again, somewhere here, I will see this point according to the y and the x, and this will go on. Once I reach here, right, the end of the screen. Once I reach here, what should be the time? Time should always keep on increasing. So I will not, like, screen has some limits, right? This is the end of the screen, right? This is the end. So screen has some limit. I cannot go till infinity. The time axis cannot go till infinity. So I have to make the time axis again to the left hand side. Okay, because in like to make it continuous waveform. So this electron, whatever the electron here, right? The electron after this, like there is a sinusoid waveform after this. Okay, this is not a good picture. This is the waveform, right? So these electrons, where will I place these electrons? Here. I cannot place these electrons here. Why? Because my screen has a limit, right? So I will again start from here. As it is a periodic waveform, I will again start from here. So what will be my force on the horizontal plate? It will be again along this. Whatever the force was here initially. What was the force here initially? 0. So that's why I have to make this 0. Make this 0. Now, ideally, what happens is, obviously this is seeing like it is instantly going to 0. Ideally it will not go like 0 because this is a continuous waveform, this is a analog system, so there will be some time for it to go. So we have few circuits and there are few names for this time, which there is a delay. So that's why this signal to go down completely to 0, it takes some time. So there is some non-idealities. So obviously CRO can never exactly give me the values, but it will give me almost accurate value. So I cannot obviously provide my waveform here. I have to start from here again. So that's why I have to make it 0. So the shape that I get with respect to this particular configuration is a sawtooth waveform. Yes, it is a ramp waveform, correct, but I have to make it 0 because my screen ends here. Okay, I don't have infinite screen, so screen ends here. So that's why I have to make the sawtooth waveform simply 0. So I have to that is the main way, that is the main name. That's why there is a sawtooth waveform and not a ramp waveform. So like that is what it is written here. A sine wave applied to the vertical plates and a ramp or sawtooth waveform applied to the horizontal differential plates results in synchronized display of the sine wave on the CRO screen. So this sine wave is actually with respect to what? T. Basically, what is my y? Basically in CRO we plot with respect to y as a function of x. That is what we do. Simply plot y with respect to x. What is my y? Y will be some Vm sine omega t. And what is my x? X is simply t, right? Because it is a ramp function. So obviously I will replace my t here. So my y will be sine Vm sine omega x. That's it. That's a simple thing. Nothing else. That's it, right? We are plotting y with respect to x. That is our main purpose. So this is giving me a sine-like function. So in the screen I will see a sine-like function. And obviously the ramp waveform horizontally sweeps the electron across the screen while the sine wave modulates its vertical position. When synchronized, the exact sine waves appear clearly on display. Obviously this is a ideal sawtooth waveform. We will not always get ideal sawtooth waveform because there will be some time for the waveform to go from this peak value to 0. It will take some time. Okay, so that basic things is given here, like that is written only. So horizontal deflection plates are positioned vertically to create horizontal electric field, enabling electron beam to deflect horizontally and generate a x-axis, that is the time axis. To move the electron beam horizontally, the electron and potential across the horizontal plates must increase continuously. This is being achieved with a sawtooth. It is increasing, but again, when I reach the end of the screen, it has to again go to 0. Then again it increases. Once the beam reaches the edge of the screen, the potential of the horizontal plate is rapidly reduced to return the beam to the origin. So assume this is the left of the screen or the origin, right? So obviously the electric field is reduced rapidly. It cannot go instantly 0, right? It will take some time. So to achieve this, a blanking circuit is connected between the horizontal plate and the cathode grate. The circuit prevents electron entry during flyback period. So what is the thing here is that this electron, right, I am providing it some field in the negative direction because voltage is reducing. So obviously if I had some electron that I am firing here at this point of time, what I will see in the screen is actually the electron I will observe that electron is like my waveform is going in the left hand side, but actually it should move on the right hand side because time function always, like time axis is on the positive side, right? But I will see that electron is moving on the left hand side. Why? Because this voltage is reducing, because I'm giving a force on the negative direction. But I should not see, as a user I should not see. This is the working principle. I have to provide a negative voltage so that it goes to 0 to the origin position, but as a user I should not see. Okay, how do I solve this? So during this this is known as the flyback period, when it is going from peak to 0. Okay, from the end of the screen, edge of the screen to the origin, it is known as the flyback period. So what we do is we don't show anything on the screen for that particular period of time. So we have an internal mechanism circuit that we use to not show that the electron is actually coming back here, the beam is coming back. That we do not show. We have a mechanism. We don't need to go into that. We don't need to understand that. Just understand that yes, there is a mechanism. So the electron, when it is here, if it is going on the left hand side or the origin of the screen, we are not able to see. As a user, we are not able to see. So how do we do that? We have a blanking circuit, and we we prevent the electron entry onto the main screen during this flyback period. We prevent the electron onto the main screen during the flyback period with the help of a blanking circuit. So that is the main purpose. So I hope you understood all these things. So yeah, that is basically it. And here few working principle is written. The fluorescent screen in the CRT is responsible for converting the electron beam's energy into visible light or luminescence, as they mentioned. The screen's inner surface is coated with phosphor, which absorbs energy from the electron incoming beam. So with the electron is coming with some kinetic energy, right? It has some speed that is being converted into light energy with the help of phosphor. It is a material that converts this kinetic energy into light energy. When electron beam strikes the phosphor, it emits light, creating a visible spot on the screen. The type of phosphor used determines the color of the emitted screen. So we can use different type of phosphors which will change the color of the screen basically. When electrons hit the phosphor screen, they release secondary emission electrons. These secondary electrons are coated or neutralized by a conductive coating called aqua DAG. So like obviously they will neutralize, right, and they will release some their energy, so that can damage the phosphor screen. So we have a coating known as aqua DAG. These are theoretical points for ESE, not for GATE. Okay. Without this collection mechanism, the screen's charge imbalance would be disrupted, affecting the display stability and brightness. Obviously, multiple electrons are going and hitting the screen, right? They have to get absorbed and they have to be totally go away from the screen, right? Because if multiple electrons are going and coming hitting the screen, it will damage the screen. So we have this mechanism, which actually collection mechanism of the electrons, excess electrons, that actually keep the screen's charge balanced. Okay, so that is the purpose. So these are the few things about the electrons. Like what is happening is multiple electrons are coming here and hitting, right, the phosphor screen. So we have some collection mechanism of this excess electrons, collection mechanism of excess electrons so that this doesn't hit the this doesn't damage the phosphor coating. So that is the main purpose, my main thing that we wanted to see. So yeah, like few more theoretical points are written, like how the flow works and all those things. This is mainly important for the ESE, not that important for the GATE. So you can go through, read this. Okay, main is the display screen, what I am interested in. The electron beam impacts the phosphor coated screen, causing it to glow. The resulting trace is a visual representation of the y-axis with respect to the time, x-axis, allowing the observation of frequency, amplitude, and other characteristics. Time-based generator. So here, right, we had a time-based generator. If you observe, we had a time-based generator. This actually generates the time axis. Okay, that is the purpose of time-based generator. The time-based generator creates a sawtooth waveform required for horizontal beam, but obviously it will have some rise time, because sawtooth waveform, right, it will have some rise time and it will have some fall time. So it cannot be totally ideal. Ideally, what should be my fall time? It will be 0, but it cannot instantly go to 0. It will take some time to go to 0. So due to that, we have this flyback circuit and blanking, not flyback period and blanking circuit to reduce that basically. So this is also important. I will also say there is a formula related to this. Due to this, which my actually output, right, there is an error. There is some error due to this, right? Obviously, we will see some error. So all this we will see. So when the ramp's voltage quickly returns to 0 and repeats the process, it forms a sawtooth waveform as shown in the characteristics. The ramp up phase ensures the beam deflects horizontally across the screen at a uniform speed. The rapid return to 0 is known as the flyback or return time, during which the beam resets to starting position. This is the period for which the beam is actually going to the starting position. So we don't show this on the screen. This is actually not showed in the screen. Not showed on the screen. Okay. So like there is one formula. We don't have time for derivation right now, and like there is a lengthy derivation. It is not that much useful to you. So just remember this formula, that how much will your electron deflect. Okay, in the y-axis, how much will your electron deflect. So this formula you have to actually remember, right? That's it. So your formula will be something like this. That is the deflection, right? The deflection will be equals to the this E like D equals to L into LD ED by 2D into EM. So what is LD? LD is the length of the deflecting plates measured in meters. So what is the length of this deflecting plates? That is LD. Okay. And what is capital L? Capital L is the length from the center of the deflection plate to this screen, point P. That is the length, right? Distance from the midpoint of the deflecting plate to the screen. D is the vertical deflection of the electron beam measured in y-axis. And what is EA? EA is actually the voltage applied at to the pre-accelerating anode measured in volts. Okay, so basically this is the electron gun assembly initial voltage that has been applied to the pre-accelerating electrons, right? And what is my ED? ED is the potential difference across the deflecting plates. So obviously I can observe from this formula that my deflection is linearly proportional to the potential difference. So obviously whatever the deflection will be, that will be almost same as the potential. So whatever potential I apply, so it will totally follow the input voltage. That's it. So this formula, unfortunately, you have to remember. How do you remember? So just remember this, that I have a deflection here, right? If this is D, then this will be LD. Okay, this much you have to remember. If this is D, then this will be LD. LLD ED by EA. This much you can remember, right? LLD ED by EA. Then you try to understand, are the units matching? So it will be LLD. LLD you remember, okay? Then ED is there. Divide by EA. So top will be ED only. It will not be EA. Okay. So EA is here. Now obviously this is not the perfect unit of length, right? You have to divide by another distance so that you get your unit as length, because on the left hand side you have deflection, that is a unit of length. On the right hand side you should also have a deflection, that is unit of length. So you have to divide by D. D is what? D is the distance between the deflecting plates. Okay. So you can remember it like a capacitor, because in a capacitor what happens? Capacitor is epsilon A by D, right? So in the bottom I have a distance between the plates. So you can remember it like that this D will come to due to this. Okay. And I know that how will you remember this 2D? This much you have to do. You have to put this in the short notes. That's it. This much I expect that this formula you have to remember. This is a very, very important formula. Now there is another term known as the sensitivity. Sensitivity is what? Deflection with respect to input. So input is my potential applied across the plates, and deflection is the deflection, basically that I am observing in the screen. So sensitivity will be deflection D, capital D, by input, that is potential difference across the deflecting plate, that is ED. So if you do this, right, you will place this ED here, it will be LLD by 2D. And what is G? G is the deflection factor. G is also known as the deflection factor. Okay. Deflection factor. So if G is the deflection factor, then definitely what can I say? It will be the inverse. Like this is the formula. It is the inverse of sensitivity. How much it like deflects the deflection that it provides for a particular change in potential. So just the inverse. These three formulas I will highly recommend you remember, and your CRO will be done. The conceptual part I have explained. The formula part also I have explained. These two things you have to do. Just these two things you have to do. Okay. So like what are the few key advantages? This is mainly for ESC. It has adjustable scales. Okay, we can adjust the y-axis voltage and time. There are knobs there. We can adjust the changes. I will show you how we do that. Fast response. Okay, no other device, analog device, is providing this much amount of fast response. Then low power consumption. It is like consuming very less amount of power. Minimal maintenance requires, unaffected by external magnetic field, because we are using electric fields, conserve electric field here, because so then we are not affected by magnetic fields. Okay, because many instruments what I have studied use the magnetic fields, right? They are dependent on magnetic fields. So that's why this is actually a good advantage of this CRO, that we don't use any magnetic fields. We use the principle of electric fields. High resolution, clear and detailed waveform, high sensitivity, high accuracy, maintenance linearity across varying signal inputs, essential for accurate analysis, because I know my deflection is directly proportional to the potential difference across the plates. Okay, so these are few advantages. So let's solve few questions. So mainly whatever formula I've told, questions will come from those formula only, nothing else. Another topic is there that will come to. Okay, but for now that formula is the most important one that you should learn. Okay, so let's determine the accelerating anode voltage. So they are asking me accelerating anode voltage, what is that? That is EA. So whenever CRO question comes, write down the formula. Write down the formula first time. Okay, so what is the formula? Formula, if I remember, D is equals to LLD, capital L LD into D, right? At the top I should have D, so it will be ED divided by 2 into small d into EA. And I know right now you have just studied, it will be easier for you to remember, but when a lot of formulas will be in your head, right, it will be difficult to remember. So that's why revise this formula every day or every alternating day or every 2-3 days. So I can say that they are asking me to find this EA. So obviously they have to provide all the other relationships with a deflection factor of 35 volt per centimeter. So they will always provide the units. From the units also you can understand what does this deflection factor means. Deflection factor, although I have already explained, D is equals to not this T only, it will be DF. DF will be equals to simply ED by capital D, but from this units also you can understand it is volt per centimeter, which is exactly correct. So it is equals to 35 here, volt per centimeter, given that the distance from the deflection plates to the CRT skin is 16 centimeter. So deflection, given the distance from the deflection plates to the CRT skin is 16 centimeter. So it is talking about this capital L distance, right? Distance from the of the deflecting plates from the CRT skin, it is 16 centimeter. The length of the deflection plate is 2.5 centimeter. So LD is 2.5 centimeter. And the separation between the plates is 1.2 centimeter. So D is 1.2 centimeter. So what is my deflection factor basically? So if I want to write my deflection factor, it is actually independent of the voltage. That's why they have not provided as the voltage. So deflection factor will be simply the opposite, right? It will be ED upon D. So all these terms will go on the left hand side and this also. So this will be 2D into EA divided by LLD. So I know D, I know LLD, I know 2. So I have to find EA and I know deflection factor. So this is equals to 35. Everything is in centimeters, so I will write everything in centimeters only. I will not change any units. Volt per centimeter, right? So now I can simply solve what is my EA. EA will be 35 into capital L. Capital L is, okay, where did it go? For some reason my mouse is not working. Capital L is 16. And then capital L is 16. LD, right? LD is 2.5 divided by 2 into D, that is 1.2. Okay, so now I can simply solve it, right? I can simply solve it. What will be my answer basically? So this will be 35 into 16 into 2.5 divided by 2 divided by 1.2. So it will be almost 583 volts. So this will be answer. So these type of questions actually do come in the examination hall. So you have to understand how to use the formula. So I've explained and few questions are there. I'll obviously solve those. Don't worry about that. Okay. So now let's come to the modes of CRO. What are different modes of CRO? There are mainly two types of mode. One is YT mode, which I have already studied now. Basically what you do in the X, right? In the X axis, I directly provide a sawtooth. So if I provide a sawtooth, what will I get? I will only be displayed the Y values with respect to time. That's it. I have already proved as well. So what we do in this mode, we observe the various parameters of the waveform of a single waveform, that is RMS, peak, average values, analyze voltage and current peaks, all these things, right? Obviously we can also understand the phase and frequency of that particular waveform, and we can measure the time period and frequency. So the number of divisions, right? So our CRO will have a screen like this. If I show CRO will have a screen like this. Now let's say, like, if you have already gone to the lab, you know about CRO. If you haven't, I will just explain just in a brief that this divisions, like there will be some specification on CRO. There will be a knob. If you rotate this knob, right, it will change the resolution. So it will change the definition of each small division. So here volt per division is 5 millivolt. What does it mean? It means per division I get a 5 millivolt, right? So one division is 5 millivolts. How many divisions I have? 3 divisions. So overall, what will be the peak to peak? This is 15. This is 15. So overall, the peak to peak will be 30 millivolts. V peak to peak is 30 millivolts. So like that, you can observe the peak to peak of a particular waveform through the CRO. Now, what about the frequency? So I will assume some like some values. Okay, so let's assume per division the time is 1 millisecond. So 1 millisecond per division. Okay, this is the unit of the x-axis. So how do we generate all those internal circuitry is there? All those things will generate. We'll just revolve the knob. We'll just rotate the knob and that's it. So how many divisions I have? 1, 2, 3, 4. So I have 4 divisions here, right? 4 divisions. And each division is 1 milliseconds. So overall, how many milliseconds I have? Total 4 milliseconds, right? Total 4 milliseconds. So time period is 4. Can I determine the frequency? Frequency also I can determine. It will be 1 by 4, that is into 10 Q, that is equals to 250 Hertz. Frequency is 250 Hertz. So all these values you can simply determine with the help of a CRO, right? So that is what I am telling here. So this is just a formula. This formula you don't need to remember. Basics, with basics you can solve, right? Number of divisions into time per division. They will provide you the time per division. You just have to identify the time period, and if you know the time period, you will be able to find out the frequency. Okay, that's basically it. So that's how you solve this type of question. Now there is one more formula that I wanted to talk about, is the rise time of the output. So this formula you have to remember. So how long does my output take to go like rise, basically? Because we have to take into the effect of rise time of CRO. Because I told you, right, it is not that ideal, right? It will take some time to increase. There is some delay there in the CRO, in the sawtooth waveform. So that delay we have to take into account. That delay will always be orthogonal to the delay of the input. Okay, how it happens, we don't have, like, it is out of the scope of the course, but just need to remember this formula, that the rise time of the output waveform, if the input rise time is given, is related something like this. It is very easy to remember. Input rise time whole square plus CRO rise time whole square whole under root will be the rise time of the output. So there will be some error. And they can ask the error as well. So what they can ask is error in the rise time of the output. Because ideally it should totally follow the input, right? So it will be practical upon ideal divided by ideal into 100, obviously. Okay, so that is how we found out the error here. So yeah, that is the thing. In XT mode, these things we only do. Now we'll study about the XY mode. So in XY mode, what we do is we basically provide signals on both X and Y axis. Now in the X axis, we don't provide time. X axis also has a signal. So in XY mode, mainly we compare two waveforms. How do we compare? It depends what type of waveform I get. So there are a few patterns that I get. Those are known as Lissajous patterns. So depending on the type of the pattern, I will be able to talk about the phase difference between those waveforms and the frequency. Okay, so these are known as Lissajous patterns. Allows the study of these patterns when sinusoidal voltages are applied to the horizontal and vertical deflection plates. Okay, so that is the case. That is what we have to understand. So these are the few Lissajous patterns. That Lissajous patterns are visual figures formed on the CRO screen when two sinusoidal voltages are applied to both the horizontal and vertical deflection plates. The application is we either use it to identify the phase difference or the frequency ratio. So I'll slowly explain all these things. First we'll understand the phase difference, then we'll understand the frequency ratio. So these are few Lissajous patterns, and depending on this type of patterns, we'll determine whether what is the relationship between the X and the Y waveforms. So there are few common shapes and patterns. If I observe a straight line, that means the phase difference between the two waveforms will be 0 degrees. So this is when the frequency of both the waveforms are same. So my Fx is equal to Fy. Only valid when the frequency of both the waveforms are same. Then I will observe a phase difference. If I am seeing a straight line, I will observe 0 degree. If I am observing an ellipse, it will be some other angle. If I am observing a circle, there will be a 90 degree of phase difference. How it comes, I will explain that. The appearance of each pattern provides a visual representation of the phase relationship. For instance, when the phase angle is between range of 0 to 90 or 270 to 360, an elliptical pattern is formed with a major axis from the first to third quadrant appears. So I will explain all these things. Don't worry about this. So let's start with the most basic case. When the two waveforms has 0 degree of phase shift and both have same frequency. So what will happen? My x of t will be, let's assume it to be sine t. Take example. Y of t, I don't have any phase difference. That is my assumption, right? My phase difference is 0 or 360. 360 means 0 only. But peak, let's say something 2 sine t. Okay. So what can I write? This sine t is what? This sine t is actually x of t, right? This sine t is actually x of t. So this sine t is x of t. So this will be 2 x of t. So y is equals to 2x I am getting. That is what? That is a straight line. That is the equation of straight line. And exactly that is what I am getting. Equation of straight line, right? So if they are phase displaced by 0 degrees or 360, I will simply get a straight line. So once you see on the screen, if I apply two waveforms and you're observing that you're getting a straight line on the screen, that means they have 0 phase shift. Okay, they are almost similar waveforms with 0 phase shift with same frequency. First observation. Let's do it for the 90 degree. If they are 90 degree, okay, if they are 90 degree, then what you'll observe is your x of t will be what? X of t will be some, and their amplitudes, their peak amplitudes are also same. That is my assumption. Their peak amplitudes are also same. X of t is, let's say, is sine t. Then y of t, they are phase displaced by 90 degrees. So their phase displaced by 90 degree. Y of t will be sine 90 plus t. That is cos t. Because I have already told, like we know this basic thing, right? Cos t will always lead sine t. Okay, this thing we know. So x of t is sine t, y of t is cos t. So let's do a few plots. There we'll understand. And anyways, we can understand this is the equation of circle. But let's do a few plots. So at t equals to 0 degrees. At t equals 0 degrees. What am I getting? I will just do a table actually. This will be the value of t. Or 0 at omega t. I will just do at omega t equals to 0 basically. This will be a short table, omega t, then this is x, and this is y. Just a short table. 0, x will be 0, y will be 1. So I will be lying somewhere around here, correct? Somewhere around here I will be lying. Then at x equals to, let's say pi by 4, right? Or 30. Let's do it for 30. 30. It will be 1 by 2 and it will be root 3 by 2. So 1 by 2 is obviously lower than root 3 by 2. Still I will be somewhere around here, right? Because 1 by 2 is very low than root 3 by 2. So I will somewhere around here. Then at x equals to 60, this will flip, right? This will be root 3 by 2 and this will be 1 by 2. So I will lie somewhere around here on the circle. How do I know I will lie on the circle? Just take the square of both these and add these two. If I take the square, x square plus y square, what do I get? It is sine square plus cos square t, right? Sine square plus cos square. Sine square plus cos square means simply 1. So it will simply be 1. Sine square plus cos square will simply be 1. Okay, that's the basic things that we understand here. So yeah, that is the basic thing that we need to understand, that sine square plus x square t will be simply 1. Now this is the equation of a circle. That's why I follow circle. And one interesting fact note here is I am going in the clockwise direction. But what if this phase shift, right, is negative? What if this phase shift was negative? What would happen then? What do I mean by negative? So if the phase shift is, let's assume my delta to be minus 90 degrees. So if my delta is minus 90 degrees, right, then my x of t, if x of t is sine t, right, if my x of t is sine t, okay, my y of t is, x of t is sine t, then y of t will be minus of cos t. It will be just a negative. So whatever values I am getting, I will just copy them and paste them. It will again be circle, because here also x square plus y square is same only, but in place of this, right, an extra negative sign will be applied. And what does it mean? It means I will revolve in the anti-clockwise direction. This is in the clockwise direction. Clockwise direction. So I will come to a conclusion later on. But for now, if you are understanding this, that if, like, there can be two cases here. Either I can lead by 90 or lag by 90. So if this delta is minus 90, I will go in the anti-clockwise. If delta is plus 90, I will go in the clockwise. So the angle direction is also very important. I'll come to a conclusion at the end, don't worry about it. For now, just understand this, that if the angle is 90, then you will get a circle. And thing to remember is both the peak values are same. Both the peak values need to be same. If both the peak values are different, then you will not get a circle. What you will get? You will get a simple ellipse. Okay, you'll get a simple ellipse. If your delta is 90, angle is 90, and both the peak values are not same, you will simply get a ellipse. How? Your x will be sine omega t, y will be 2 cos omega t. Okay, so if you do x square plus y square, right, you will get back some equation of ellipse. So like this will be almost like equation of ellipse only, because what you will get is this will be sine square omega t plus 4 cos square omega t plus 4 sin omega t cos omega t. Sin omega t cos omega t this is equals to what? This if I do this x square plus y square, right, because there it was always equals to 1, I was equating it with respect to 1, that is always equals to 1, but this is equals to basically my x square plus y square, correct? So a portion of this is actually 1 and a portion of this is not 1. So overall, like if you solve this, you will get a equation of ellipse. So do note that when the magnitudes are same, you will get a circle. When the magnitudes are not same and the phase shift is 90, you will get an ellipse. And if the phase shift is not actually exactly 90, it is between 0 to 90. If it is between 0 to 90, you will always get an ellipse. You will always get an ellipse. How? Your x of t is a sin omega t, y of t is b sin omega t. So one thing you have to understand, when you will always get an ellipse is if your a is equals to y. So if you simply solve this, right, if you simply again do the same analysis, omega t, x and y, if you just plot the values, okay, x and y, you will see you are getting like a ellipse function. You can plot it. That is the homework task for you. Plot it. And anyways, if you solve this, right, you will get a equation of ellipse. That is proof. That is the mathematical proof. We don't want to waste the time. So this will be ellipse. So if your angle is between 0 to 90, you will get ellipse. But remember, it will be in the clockwise direction. So sir, then what about in the other direction? I'll talk about the anticlockwise. Don't worry. Okay. But if your angle is between 90 to 180, if your angle is between 90 to 180, you will get ellipse again. Obviously, these two magnitudes has to be same. You will get an ellipse, but this ellipse is in the first and third quadrant. Like its major axis, right? If you observe, its major axis is lying on the first and third quadrant. Correct? Minor axis is this, but its major axis is lying on the first and third quadrant. But its major axis, if your angle is between 90 to 180, this is on the second and fourth quadrant. So how do we remember this? So obviously we will not prove right in the examination all. So you can remember it like this, that angle is between 0 to 90. So my major axis will be between 0 to 90. Okay. So major axis between 0 to 90, that means the major axis is in the first quadrant, and with first I get third quadrant. So angle is between 0 to 90, that means my major axis will be between 0 degree to 90 degrees. Okay. So that's how you remember. Simple, right? Here angle is between 90 to 180, and always remember this is for the clockwise. This is for the clockwise case. For the anti-clockwise, I will tell you this for the clockwise case. Okay. So if my angle is between 90 to 180, basically my major axis will lie between 90 to 180. What is 90 to 180? 90 is this, 180 is this. So obviously I will lie here. So it is lying in the second quadrant, right? Angle is between this, so major axis will lie in the second quadrant. Okay, so it lies in the second quadrant. So that is a basic thing. That you need to understand. That's it. That's done, right? And obviously with second there will be a pair that will be the fourth quadrant. Okay. So you can obviously derive. We don't have time, so we won't derive. That's the basic thing that you need to understand. Now, if the angle actually increases more than 180, what will happen? If the angle is exactly equals to 180, again you will get a straight line, but again, as the angle is 180, right, you will get a straight line in the second and fourth quadrant. So here what it means, your delta, right, delta is 180, so that means your y will be equals to minus of x. That means there is a phase shift of negative. It is almost equals to x, but it is just the opposite sign. So that's why your major axis will, like your like all straight line will lie in the second and the fourth quadrant. Okay, these are few summaries. Now let's come to for theta greater than 180. For theta greater than 180, what you have to understand is theta is between 180 to 270. So if theta is between 180 to 270, whatever will you follow, right, that will follow here opposite, because theta 180 to 270 means in this quadrant, but actually it will not lie in this quadrant. Major axis will not lie in this quadrant. Major axis will lie in opposite quadrant. Why? Because we have been increased from 180. Whenever we increase from 180, it becomes negative, right? Just I'm telling you a way to remember. This is not something conceptual thing, just telling you the way to remember. So when I increase from 180, my major axis will be just the opposite. So this time from here I can understand that it is telling 180 to 270 is somewhere here, but I will not follow this. I'll follow from previously I was going from this axis, right? Whenever I will increase my angle more than 180, I will go from this axis. So 180 to 270 will be somewhere here. So previously I was following this axis, right? I was following from the positive x axis. So now I'll go towards the clockwise direction. Now I'll go towards the clockwise direction. So if I go towards the clockwise direction, my major axis 180 to 270 is this particular quadrant, which is basically the second and fourth quadrant. Okay, and do remember this will be in the anti-clockwise direction. How you can derive? Obviously you just put the values, you just put a table of values. You will see I'm moving in the anti-clockwise direction, not in the clockwise direction. Just in the just like in the circle case, right? I had two angles. So obviously if my angle is exactly equals to 270, I will get a circle again, but in the anti-clockwise direction, just proven here, right? What does 270 means? What does this minus 90 means, right? What does this minus 90 means? If I just add 360 with it, I will get how much? I will get 270. So if you are ever in a place of bother, okay, and if you are worrying, you can always derive this. Circle deriving is not that difficult, but ellipse is difficult, right? If you are in a place of bother, right, you just take two signals, make their magnitudes equal, A sine t and B sine some angle t, right? Let's say if you have solved and you are getting delta as 270. So you write here 270, not let's say assume it as 300. You write here, then put few values and plot in the graph in the rough notebook, right? Plot in the graph whether you are observing the same pattern that is given in the question. If you are not observing the same pattern, then your derived answer, solved answer is wrong. So that's how you cross verify. That's how you cross verify. So I have told you that as well, how to cross verify in the examination hall. This you do only if you have time, because this will take time, right, to put the values and right. This you do at the end. Okay. So yeah, that is how you can cross verify. If you ever forget, you have the option get out of jail card as well. So that is the thing that I want to explain here. So yeah, in this will be a circle and just it will be in the anti-clockwise, not in the clockwise, just like the plus 90, not in the clockwise direction. Now if I get an ellipse like this, if my angle is between 270 to 360, now my axis, major axis will lie in the first and the third quadrant basically, because that will be the direction, like that is where the major axis will lie. So these are few things, and here is the summary I have written. You can go through the summary or just try to understand the explanation how I have explained. That is the important part. Just one thing you have to remember is that if my phi is ever greater than 180, I will get a encirclement in the anti-clockwise direction, and if my phase difference is less than 180, I will get an encirclement in the clockwise direction. That's the thing you need to remember. And for 0 to 360, you understand that it is a straight line. For 0 to 90, you understand it is a ellipse if the amplitudes are not equal. If A is not equals to B, if A is equals to B and the angle is or 90 or 270, I will get a circle. It will be either clockwise or anti-clockwise depending on the values. 90 means it is in the clockwise direction, 270 means it is in the anti-clockwise direction. 90 to 180, again I will get an ellipse, but my major axis, right, major axis will lie in the second quadrant. So this is quadrants for the major axis. Right here, major axis quadrants. Okay, so that is the case here basically. So now how do we exactly find out the angle? Because from I know the x and y, I can tell like what is the phase difference, but from the screen how can I exactly talk about the angle? That I will explain, right? So there is a formula. That formula is what? That your angle, phase difference angle between the two ellipse, right, will be phi will be equal to sine inverse x1 by x2. Now what is x1 and x2? x1 is the x-intercept, right? x1 is the x-intercept and x2 is the maximum x value that this ellipse reaches. This is for case of ellipse. This will work in circles as well, because circles is just a edge case, right? Well, my x1 and x2 are same, correct? Maximum x value and the x-intercept are same, so it will work for circle as well. Okay, so here what I can say is that now how can I remember this formula? So you can equate this with y1 y2 as well. This is the most important part. This you have to put in short notes. Okay, how do you remember this? This also equals to sine inverse y1 by y2. Okay, so one thing you can remember is you understand that sine, right? Sine inverse of anything, this x value or this some z value, right? This z always has to be less than 1. It can never go greater than 1. Then it's an invalid function, because sine gives me always something lower than 1, right? It can never give me something higher than 1. So obviously this value has to be lower than 1. So I remember that it has a ratio x of x or y. Both are x or both are y. But how do I remember which one comes at the top and which one comes at the bottom? Simple, right? Because x1 will be the lower value. It is the x-intercept. For ellipse, x-intercept will be lower than the peak value. Like from the name represents, right? It is the maximum value. x2 is the maximum. So maximum will be in the bottom. And x1 will be at the top. Just change the color here. This will be at the top, right? x1 x-intercept will be at the top, because this ratio only satisfies the condition of getting a value less than or equals to 1. That is the only equation that satisfies. So that's why I get x1 by x2 equation like this. So I hope you understand how to remember this formula. Now this is for the clockwise case. What about the anti-clockwise case? If your encirclement is in the anti-clockwise, you just have to subtract a 360. That's it, because both angles will be same only almost. 90 and minus 90, right? Minus 90. You remember these two cases, 90 and minus 90. How can I represent minus 90? Minus 90 I can represent plus 360. So minus 90 plus 360. What is it? It is 270. So 270 in terms of 90 is what? 180. 360 minus 90, right? 360 minus 90 is also like 270. So that's how you represent. So always represent. For clockwise, it will be just the normal formula. For anti-clockwise, you just do 360 minus 5. Minus 5. That's it. Okay, I have told you how to remember. I've told you how to remember the anti-clockwise as well. So I tell you how to remember the formulas as well, right? So case 2, when I have an ellipse at second and fourth quadrant. So if I have an ellipse at second and fourth quadrant, how can I remember again? So this time, just remember there will be one extra factor of 180 here. Why? Because my major axis is lying on the second and fourth quadrant, correctly. So how you remember? You remember it like this. This term will be constant, but this time it will be 180 minus 5. Okay, 180 minus 5. Why 180 minus 5? Why minus 5? Because my y is positive here, but my x is negative. Here my y is positive, x is negative. So that's how you remember, right? So sine inverse something negative and something positive. Overall it is negative, right? So overall angle will be also negative. That's why minus 5. So major axis is here. So what is happening? Either the signs of y and x are opposite. So xy is always less than 0. Currently signs are always opposite. So obviously that's why I will get a negative angle. I'm just telling you a way to remember, nothing conceptual here. Okay. So 180 minus 5. 5 is this. I have already explained how to remember 5, and that's it. For clockwise. What about anti-clockwise? Just do 360 minus this. Just do 360, right? 360 subtracted by this. That's it. So which formulas you will remember? This formula and this formula. These two you will remember. And the other two will be just 360 subtraction of that. That's it. For anti-clockwise, just do 360 subtraction. So just remember, for anti-clockwise, just do 360 minus whatever angle you remember. That's it. Okay, that's how you remember. Now there is another, like this also I cannot, like we don't have scope to derive this. Now if the frequencies are different, okay, if the frequencies are different, how will I compare the waveforms? So actually I can compare the ratios of the frequencies. So omega h means the horizontal like plates, the frequency of the horizontal plate waveform, and omega v means frequency of the vertical plate waveform. Omega h upon omega v will be fh upon fb. Okay, that will be equals to nv upon nh. So what is nv and nh? Nv and nh is the number of horizontal tangencies of the waveform. Okay, of the waveform that I see from the CRO screen, of the CRO screen. This is all of the CRO screen. This is also of the CRO screen. I'm talking about the tangency of the CRO screen. Okay, so it will be omega h upon omega v, that is fh upon fb. So nv upon nh. Nh is number of horizontal tangencies, nh is number of vertical tangencies or number of intersections with the vertical lines. Like I will show an example and there we'll understand this. Okay, so here I have a waveform. So let's solve a very simple waveform first, then I will solve the difficult one. So let's say the CRO screen, right? CRO screen gives a waveform like this. I will show you like this, and another like this is x, this is y. This is the CRO screen waveform that I'm observing, and I have another pattern. This is y. Just hold on. This is the pattern that I'm observing. Okay, so okay, this is also not totally horizontal tangencies. I can like this pattern, any pattern you can take. Now, how many vertical crosses I have? Like just draw a horizontal line. Just draw a horizontal line and see how many times I'm cutting the waveform. I'm cutting the waveform here and here. So NH will simply be 2. Okay, that's it. Just draw a horizontal line that is parallel to the x-axis, and how many times I am cutting the waveform. Like that you can calculate NH. There is other way to calculate NH as well. How you can calculate? Just draw tangents, right? Lines that are tangent to the waveform. How many horizontal lines that are tangent to the waveform? 2 horizontal lines. There are 2 horizontal lines that are tangent to waveform. So either way you find out the tangent formula or the cutting of the waveform, you will get 2. Now, what about vertical? Again, if I just draw a vertical line, how many times am I cutting the waveform? Ny is simply 2. But if I want to draw the tangent, right? Tangent will be parallel to the y-axis. So how many tangents I have? 1 and 2. So 2 tangents. So although this is circle, I already know the waveform basically. So I know that my frequency ratio omega h by, remember, this is the opposite. Right here, if I have h, this will be the opposite. So this thing also you have to remember, right? It will be opposite. Not here. I don't want to do there. Okay. So it will be omega h upon omega v. Okay. So it will be opposite, right? The number of vertical tangencies, or I can write this as vertical, that is 2 divided by number of horizontal. 2 by 2, that is 1. Although I know this is circle, so they will obviously have the same frequency, right? But what about this waveform? What about this waveform? So now if I choose, if I take a horizontal but vertical line, I am observing that I am cutting the waveform here as well too, here as well too. So obviously I have to see the maximum number of cutting of the line. I will choose a vertical line such that I am cutting the this loop maximum number of times. Okay, that I have to observe. So here I am seeing maximum number is 2. So NV is 2. What about NH? And if I want to draw the tangent as well, if I want to draw the tangent, right? Tangent I can draw here and here. So there are 2 tangents. Again, or 2. Okay. What about the horizontal one? Horizontal one, NH will be simply again, if I just cross over a line, that is this, I am crossing it again here once, here once, here once, here once. I am crossing it 4 times. Okay. So you cannot choose a horizontal line here, right? You cannot choose a line here where it is crossing itself, where the loop is crossing itself. You cannot choose a line here. You have to choose a line here only. So it is actually 4 times. So that is one thing I wanted to say, that if I choose a line here, right, it is a wrong line. It is not a correct line, because you cannot choose a line where the loop itself is intersecting. So I will write here, we cannot choose a line where the loop itself is intersecting. Okay. So how many vertical? I get 2 vertical tangents, right? Okay. So how many horizontal tangents do I get? So this is 4. So NH here is 4, and this is one of the tangents. This is one of the tangents. This is one of the tangents, and this is also one of the tangents. So total I have 4 tangents. Okay. Although this drawing is not perfect, I will go to a perfect drawing in the next slide. So there you will understand we have total 4 tangents. So obviously now I can say that my omega v upon omega h will just be the opposite, right? It will be nh upon nv. So nh is 4 upon 2. So this is 2 simply. So we'll get 2. So the frequency difference will be simply 2. Now let's go to an actual question which came on Git. So this will also better clear your idea, right? So here, how many, like they are just asking the frequency difference. What is the relationship between omega and omega 2? That I will come to later on. I'll just want to draw the lines. So how will I draw the horizontal lines? Horizontal line is here, right? You can either draw here or here. Either one works. Okay. So if I draw here, how many number of cuts I am getting? 2 number of cuts. Okay. I cannot draw here because this is the point of intersection. I cannot draw here. So my NH will be 2, or they have written P1 of t. P omega 1 of t is a sin omega 1 t. Why is it? Omega 1 means x. X is mapped to this. So that is horizontal. So this is basically n1. I'll write this n1 for my better understandability and readability. Nv is basically equals to n2. That is this, right? I can place here or here, either way. It is cutting 4 times. Okay. So now, how many horizontal tangencies are we getting? Here if I observe, the number of horizontal tangencies are here. Okay. And here there are 2 horizontal tangencies. Number of vertical tangents, this is one of the 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 tangents. So I have total 4 tangents. So either way works, right? So now your ratio of omega 2 by omega 1 will simply be n1 by n2. So n1 is 2, n2 is 4, so it will be simply 1 by 2. So omega 2 will be omega 1 by 2. So that's it. That is the solution written over here, right? So it will be option B. Option B will be correct basically. Okay, so that's how simple question is. So we can solve using when the loops are not closed. Then also things become very interesting, right? If the loops are not closed here, how many horizontal and vertical lines I have? So whenever you see, right, this is half, you will assume it to be, like if you are solving using tangents, you will assume it to be half, because this is not completely closed. There is other side, right? So first I will solve it in 2 ways. One way is using the cuts. How many cuts I have? How many horizontal cuts I have? Total, if I see, I have total 3 horizontal cuts. So nx equals to 3. How many vertical cuts I have? Vertical cuts I can observe only 1, right? Ny equals to 1. I cannot get any other cut. It is not a closed loop. What about if I want to solve it using tangents? So here, this is almost like a tangent, but this is not a closed loop, right? So I will assume it to be like, that is the procedure, that is the method. I will assume it to be half a tangent, okay, on the horizontal direction. This is also half a tangent, and this is obviously, here I have a tangent and here I have tangent, right? So 2 plus half is simply 3, getting the same result. And how many horizontal tangents I have? So this is half a tangent, and this is again half a tangent, right? Horizontally. Do I have any other tangents? No, I don't have any other tangents. So the ends, right, you assume it to be half. That's the procedure. That's the method. So this will be again half plus half. So I get 1. So I get the same result. I get the same result as using solving the cuts. Either way, it works. Okay. So here are a few questions that I want you to try. And in the next lecture, I will solve all these questions. And in the next lecture, we'll study about digital voltmeter and Q meter as well. So all this, please pause the video and try by yourself. And in the next lecture, I will solve all these questions and also few extra questions as well. Like all these questions I will solve, and obviously we'll study the topics, that is digital voltmeter and the Q meter. Okay. So these are basically few questions that I wanted to solve. Few are gate PYQs. Okay. And yeah, you can solve this, then this. Pause the video and try to solve. And in the next lecture, I will solve all these questions together. Okay. So yeah, that's it basically for this lecture. And in the next lecture, I will solve all these questions and obviously the Q meter and the digital voltmeter. Few remaining topics we'll solve from this particular chapter. Thank you for watching, and I'll see you in the next lecture. Hi everyone, and welcome back to PrepFusion. I'm Anish, and today we'll start the lecture 2 of our CRO and DVM and Q meter chapter from measurements. So we have learned what is a CRO, how it works, what are the underlying principles and the formulas, important formulas. Okay, I summarized everything. I'll just quickly go through the previous lecture. We learned mainly the working principle is fine, right? That is the one part. Okay, but in gate, sometimes working principle won't be asked, obviously. The questions will be asked. So questions can be of two types. One is this type where you are firing time in the x-axis and like the waveform in the y-axis. So if you are doing that, then you have to use this formula sometimes, because time period will be number of divisions into time per division, or like the y peak to peak, right? Also we have solved a question like that, y peak to peak. That also is number of divisions into the peak to peak voltage per division, right? And another formula that can come is the deflection. How much will be the deflection, or what is the anode accelerating voltage, or what is the deflection voltage? All these things can come with this formula. So with this formula you have to remember, and then from this you can easily identify the sensitivity, and with the help of sensitivity you can find the sensitivity of any CRO, and the inverse of sensitivity will be your deflection factor. So these three formulas are mainly important if you are firing, if you are making the CRO work in the first mode. What was the mode 1? Mode 1 was, I think, here YT mode, where x-axis was the time axis and y-axis was the what do you say? Y-axis was the like Euro waveform. I think it is written somewhere around here. Because yeah, here, right? YT mode, correct? So this is the question that can come from YT mode. Now from XY mode, there can be two cases. Either the two signals are has same frequency or different frequencies. If they have same frequency, that means they can have a different phase difference, right? Their peak values can also be differing, and their phase difference can also differ. But before that, this was one formula that was related to the rise time of the output, because obviously, you know, if you remember correctly, the CRO, the x-axis electrons of the CRO comes here and then goes back here, right? There is some delay here to come back, right? Or there is a delay to rise the sawtooth waveform. There is some delay. It doesn't rise instantaneously. So obviously we have to take into consideration the delay, and the formula is given here. So we don't have time to prove this. So just remember this formula. This can come. Mainly this is more important for EAC, because EAC can ask some weird questions from weird formulas. So mainly for EAC, but GATE can also ask this question. Okay, so next is XY mode, as I explained. So XY mode, there are Lisa-Jones patterns. So if they are in same frequency, then their phase difference will be differing, and how they are differing, how to remember the formulas, that also I have explained here, right? All these things. So summary is written over here only. Summary is written here, right? You have to just remember these formula. If you remember this, 360 minus this angle will give you the anti-clockwise encirclement, right? This is the clockwise encirclement, and 360 degree minus is anti-clockwise encirclement. Now, one you have to remember, unfortunately, you have to remember something, and with the help, with the keeping this as reference, you can derive all the others. Now, this is for the quadrant, first and third quadrant. Okay, if your ellipse is lying on the second and fourth quadrant, then this your phi will be 180 minus phi, right? This 180 minus phi basically, and your other, if it is if it is clockwise basically, and if it is anti-clockwise, then obviously you have to do 360 minus of this thing. Okay, 360 minus of phi dash. I can say phi dash. This is not phi. 360 minus of phi dash. Okay, so this is my phi dash basically. Just hold on. Okay, so this is how you remember. These are the four formulas that you like. One formula you keep as reference that you remember, and derive all the other three formulas with respect to that reference. I think this one would be the best suited one. Okay, so next, if they are of different frequencies, obviously their ratios of frequency will be the number of horizontal tangencies by vertical tangencies, basically the opposite tangencies. If it is horizontal, this will be vertical, number of vertical tangencies. If this is vertical, this will be horizontal, just the opposite ratio. Just take the ratio and you will get the ratio of the frequencies. Okay, so I told you how to calculate those tangencies as well, and we solve the questions, right? So now we'll solve today's questions basically. So we have given x and y, the resulting CRO plot will be basically x versus y. So here, if I observe, I can observe there is a 90-degree phase difference. If you do this, you will observe there is a 90-degree phase difference, and you will tick mark a circle, because in a circle, if the peak values are same, and if there is a 90 degrees phase difference, it becomes a circle. But actually, you don't observe the question properly. This is actually not 90 degrees phase difference. Why is this not 90 degrees phase difference? Because this is cos and that is sine. So cos and sine itself has some phase difference, correct? So this is not 90 degrees phase difference. Okay. So what is the actual phase? So you either take a reference. Okay. So what you can take a reference is sine. We can take sine as a reference, right? If sine is reference, generally if you tend to forget what is the phase difference angle between sine and cos, you can do here cos. This is not cos. This is cos. And this sine. Generally, this is how I try to remember it. So cos is here and sine is here. So I will take sine as reference. So what will be cos basically? Cos, I have to get to sine, like what is cos to sine? So if I do sine omega t plus 90, because I have to add 90 degrees to sine, I will get to cos, right? So that's why I have added 90 degrees. So I will do this transformation only, right? I will do this transformation only here. So here, this will be like y of t. I can write it as 10 cos, not cos, sorry, sine of omega t plus 90 minus 30. Correct. So this will be sine 10 sine 50 pi t plus 60. So this will be exactly equals to x of t. Okay, this will be exactly equals to x of t. This will not be like there will not be any phase difference. And what happens when there is no phase difference? It will be a straight line. Correct. So this is wrong. This is correct. Now if there was a phase difference of 180, what would have happened? It would have been a straight line again, but it would have been in the second and fourth quadrant. Correct. So let's do this. We have to find the phase difference of the signal, right? So again, if I forget that what, like the formula was generally for the first, this is x and this is y, correct? And this is my first quadrant and this is my third quadrant. So my formula for first and third quadrant, my phi was equals to sine inverse x1 over x2. Now what is x1 and what is x2? What if you forget? In the previous lecture also I explained how you can recall if you forget this, what is x1 and x2 supposed to be. So whatever is inside sine inverse, right, it should be always less than 1. So x1 can never be this value. If x1 is this value, or like y1, this is equals to y1 by sine inverse y1 by y2. Y1 can never be this value. If y1 is 4 and y2 is 2, then it becomes sine inverse 2, which is invalid, right? Which can't happen. So obviously this one will be the y-intercept, y1 will be the y-intercept, and y2 will be the peak value of the y. Okay, so this will be equals to sine inverse 2 upon 4, sine inverse 2, that is 30 degrees. Okay. But again, you will be wrong. Why you will be wrong? Because you again forgot that this was for clockwise. And here I can observe my wave has anti-clockwise encirclement, my loop. So obviously the formula for this was phi dash, I will keep that as reference, will be 360 degree minus phi, right? For anti-clockwise, it's just 360 minus phi. So 360 minus phi, this will be equals to 360 minus 30, that is 330 degrees. Okay, so yeah, that is the case here. So next, like this was a simple question only, but you can make silly errors, and this will cost you. Like these are so easy questions, everyone will solve you, but you will not be able to solve due to some silly mistakes. So don't make these silly mistakes. That is the one thing that I wanted to give you in this like solution of the question, right? Questions you can solve, formula is there, you can put the things in formula, but where you can make the mistakes, that is the most important point that I want to stress. Now, a sinusoidal waveform displayed on a CRO screen has a peak to peak amplitude of 20 centimeter. So V peak to peak, correct, is 20 centimeter. Or this is equals to what? 2 Vm, right? Peak to peak of a sinusoid is 2 Vm, right? Vm from 0 to Vm and from 0 to minus Vm. So 2 Vm into what? Into divisions or volt per centimeter. So what is the small division in the y-axis? Volt per centimeter. That I have to multiply, right? Then only this will be converted into volts basically, because this is my V peak to peak. Sorry, yeah, this actually is 20 centimeter, or this is, just hold on, equals to 2 Vm. V peak to peak will be equals to 2 Vm, will be equals to 20 times, like the distance of peak to peak, 20 centimeter times volt per centimeter, whatever the volt per centimeter is. What is the volt per centimeter? They have already given the vertical sensitivity, which is 2 volt per centimeter. So simply I have to multiply this to get to my actual volts. They have asked for the RMS. What will be the RMS of the signal? RMS, VRMS of a sinusoid is what? It is Vm upon root 2. Okay. So this will be 2 Vm is 20 centimeter into 2. So Vm will be 20 volts basically. And what about your like they want RMS, right? So VRMS will be what? It will be 20 upon root 2, that is 10 root 2, so 14.14 volts. So in CRO, right, whatever question will come, very simple questions will come. Just don't make any silly errors. That is the one thing. Just don't make any silly errors. Okay, so this is the answer. So now let's solve this question. A CRO is operated in sweep mode to test a time varying signal ST. Okay, the signal displayed on the screen while in AC coupling will be. So whenever like a signal time varying signal is given, so it is a combination of DC plus AC. Whenever they say the signal displayed on AC coupling means DC is uncoupled, DC is not present. So we are just removing the DC. No DC. In AC coupling, there will not be any DC. So basically, if I just remove the DC, I will be left with only the AC signal, that is this. That is 250 sine 50 pi t. So only on the option C, we have 250 sine 50 pi t. Okay, that's it. That's simply it. Correct? Now, like this is a very, very simple question. This can be asked in ESE, not in GATE generally. A CRO is it is used to observe a sinusoidal signal with the following parameters. Amplitude 10 units. 10 units meaning y-axis amplitude, that is Vm. Height of Vm, right, is 10 units. But actually what is 1 unit equals to, that I have to multiply to get it into volts. That is into volts per unit. So what is a unit like in the scale? Because my scale will be something like this, right? This will be 1 unit, this will be 2 unit. So what is each unit defined? How many volts is each unit? That I have to put here, volts per unit, and then only I will be able to get the value of the amplitude on volts. Frequency is 50 Hz, so that is fine. F is 50. Phase angle phi is 30 degrees. Okay. The time base setting is 2.5 milliseconds per division. So the milliseconds per division in x-axis is 2.5. Correct. The CRO displays 10 cycles of the signal. The number of divisions on the CRO on the screen will be. So actually I don't even need this information. I only needed the last line. Okay. So what are they telling that the time base is 2.5 milliseconds per division. Okay. So that is the each unit defined. So each x-axis unit, right? So this is 1, 2. So each unit of the x-axis of the CRO is defined in terms of time as 2.5 milliseconds. And what it is telling, it is telling that the number of it is telling the CRO displays 10 cycles of the signal. 10 cycles. So how much is 10 cycles in time, in terms of time? So what is one cycle? One cycle will be simply 1 over f, right? So that is 1 over f is 50. 1 over 50 is 20 milliseconds. So it is 20 milliseconds. So one cycle corresponds to 20 milliseconds. So what will be 10 cycle correspond to? 10 cycle will correspond to simply 20 into 10 milliseconds. Correct. So 10 cycles correspond to 10 milliseconds. So actually my CRO is displaying 10 milliseconds, 200 milliseconds. Okay. In the x-axis. CRO is displaying 200 milliseconds, but it is not asking that. It is asking, can you tell me how many divisions are there in the CRO on the x-axis? So how do I solve it? So I know the total duration for which CRO is displaying is 200 milliseconds, and I know 1 unit distance is 2.5 milliseconds. So how many units I have on the x-axis that the CRO is actually displaying? So that is what is asking, right? So I know 1 unit is 2.5 milliseconds. Sorry, I know 2.5 milliseconds is 1 unit. So how much is 200 milliseconds? Because my CRO is displaying to 10 cycles, 10 cycles correspond to 200 milliseconds. So I need it in units because they have asked how many divisions it has. Basically, how many units it has on the x-axis. That is what it is asking. So it will be 1 by 2.5 into 200. Correct. So it will be 40. Okay. So is it 40? Okay, 40 is for 100. 80. It will be simply 80 divisions. Okay. 80 divisions. So answer will be 80. So it will have total 80 divisions on the x-axis. Okay, so sometimes they will give you some irrelevant information, but still you have to read and note everything down. It may be required, it may not be required, but what we require was only this information and this information and this one, right? 3 information. Okay, everything else is useless to us, but still you have to write it down. So this is a good question. Just try to understand what the question is asking you. That is the important point. Now next question is also very good. You try it by yourself. Okay, an electrically deflected CRT has a final anode voltage of 200 volts. Okay, anode voltage meaning this is final anode voltage of 200 volts, which is in the formula what it is EA, the accelerating anode voltage, right? This is what it is talking about, with deflecting plates that are 1.5 centimeter long. So the length of the deflecting plates LD is 1.5 centimeter long. So these type of question, right? CRO questions, generally you have to use formula. So whenever there is formula, just write down what each terms mean in the formula, right? What is equals to each term, what is the value of the each term, then just put it in the formula. That's it. But this is a new type of question where I haven't explained the formula, so you have to derive with basics. So and 5 mm apart. So D is 5 mm. Okay, if the target screen is positioned, sorry, this is LLD, yeah, LLD, yeah, this will be actually small LD. In the formula I have defined it like this, I will not change it. If the target screen is positioned 50 centimeter from the center of the deflecting plate, so what is the distance between the center of the deflecting plate and the target screen? It is 50 centimeter. So capital L will be 50 centimeter. Calculate the beam speed. Okay, how do you calculate the beam speed? So what is happening is that the electron, right, as soon as it comes in the electric field, it gains some potential energy. Okay, it gains some potential energy. So electron so here I have deflecting plates, right? So they are producing some electric field, and my electron is here. As soon as the electron comes into effect of this electric field, it gains some potential energy. Okay, and as soon as it gains the potential energy, that gain in potential energy has been converted into kinetic energy, because it again accelerates on a particular direction, whichever direction the electric field is, correct? So when electron reaches the vicinity of electric field, it gains some potential energy. Now as soon as it reaches on the edge of the CRT, right, on the edge of the screen, so all of that potential energy will be converted into a kinetic energy. Whatever potential energy it has gained will be converted into kinetic energy, right? So when it reaches near the screen, all the potential energy will be converted into kinetic energy. Basically, we have to apply the law of energy conservation, because energy will always be conserved. So whatever the potential energy the electron had, that will be totally converted into kinetic energy. So what is the potential energy? Potential energy of electric field is Q times V, if you remember. And what is V? V is the anode accelerating voltage, because that is the voltage that has been applied between the two plates, and that is what my Q is coming across, right? So it will be Q times VA, which will be equals to half ME VE square. That is the electron velocity, correct? So what is Q? Q is simply E, right? Electronic charge. It is 1.6 into 10 raised to power minus 19. In gate, most probably they will give you the mass of electron, because generally you tend to forget the mass of electron. Don't tend to remember it. But electronic charge you have to remember, 1.6 into 10 raised to power minus 19 coulomb into volts. What is accelerating voltage? Accelerating voltage they've given me as 200 volts, right? 200 is equals to half mass of electron. What is mass of electron? They will give you in the question, but here obviously I remember it, 9.1 into 10 raised to power minus 31. It is that low. into V square. Correct. So obviously, if you haven't studied electrostatics from me, please go and study electrostatics from me. This will be more clear, right? This concept will be more clear there. I highly recommend you go and study the electrostatics from me. Okay. So your velocity, if we just solve this particular thing, right? I'll just quickly solve it. This will be 3.2 into 2, that is 6.4 into this 10 raised to power 17, right? 10 raised to power minus 17 and plus 31 minus 17, 14 whole under root. Okay, so what will be this equals to basically? So I can quickly compute this. So this is 6.4 into 10. If I do this will be okay 60. If I do 640 under root, yeah, this will be 25.3 into 10 raised to power 6 meter per second. So this will be the part 1 basically. This will be the speed. Okay, this will be the speed. Am I doing something wrong here? That is what I'm trying to observe. Mass of the electron. Okay, I forgot to divide by 9.1, right? Okay, forgot to divide by 9.1. So 9.1. Okay, 25.3, 9.1 whole under root to 25.3. Yeah, this will be 8.38. Okay, so it will be 8.38 meter per second. This is the beam speed of the electron. Beam speed means what? What is the speed of the electron basically? So this is the part A basically, beam speed, right? Now from here, can you calculate the sensitivity? What have they asked? They have asked the deflection sensitivity. What was the formula for deflection sensitivity? Deflection sensitivity was equals to D by E D, right? The voltage across the deflection plates. Now what was the formula for sensitivity? Sensitivity was LLD into ED divided by 2 D into EA. Correct. So my D over, so this is not S, sorry, this is the so this is the deflection, right? This is a deflection. 2 into small d into E. So my ED over D will be what? It will be simply it will be LLD divided by 2D into EA. So LLD, L is 50, I believe. I just wrote it down. It is 50, right? 50, so everything I will write in centimeters. I will not write in millimeters. So 50 into LD. LD is how much? LD is 1.5 centimeters. Divided by 2 into small d. Now this is in millimeters, right? 5 millimeters. I will write this in centimeters. So it will be 5 into 10 raised to power minus 1 in centimeters into EA. EA accelerating voltage is 200, anode accelerating voltage. So now I will simply solve this. So just hold on. If I just simply solve this, right? So 50 divided by 200 into 1.5 divided by 2. So this will be around okay, divided by 210. Am I doing everything correctly here? Just hold on. 50 into 1.5 divided by 50 into 1.5 divided by 200. Yeah, 0.35. Yeah, this should be 10. Yeah, 0.35, right? This should be 0.375 centimeter per volt. Remember the units. Don't mess up with the units. Okay. So this is my sensitivity. part B. What about the part C? Part C is they are asking the deflection factor. It is just the inverse of sensitivity, right? So inverse of sensitivity is, that is my G. It is, or G, or sometimes we write it like the deflection factor DF 1 by S. So it will be 1 by 0.375. It will be 2.67. What is the unit? Unit is volt per centimeter. Okay, don't mess up with the units. Gate can play with units. They can ask volt per millimeter. Okay, they can ask that also as well. So let's solve this next question. This question was very good. You can go through this question again. The probes of a non-isolated 2-channel oscilloscope, okay, are clipped to points A, B, and C. So one of the probe is here, one of the probe is here AB, and another probe is here C. Okay. V in is the square wave of a suitable low frequency. So V in is a square waveform. So input is a pulse like square waveform, right? Input is a pulse like square waveform. Input is a pulse like square waveform. Next, the display on the channel 1 and channel 2 are as shown on the right. So channel 1 has this display and channel 2 has this display. Then the signal and ground probes are S1, G1, S2. So obviously there are 3 probes. One will be signal and another one will be ground probe, and another one will be signal to S2 probe. Okay, here of channel 1 and channel 2 respectively are connected to points. So then these probes, right, are connected to what points basically? That is what they are asking. So channel is to connected between what? Like there are 2 oscilloscope. I have 2 channels on the oscilloscope, and I have one ground pin. Okay, that is common to both of them. So ground is common, right? Here I can observe ground is common to both of those pins, and the other probe is basically connected to either here or here. This I can assume as ground. Okay, so where are each probes connected? That I have to measure. Correct. So if I observe this, right, this is something negative because this is by 0 axis, right? This is ground. Ground is 0. So this is negative. So channel 2 has voltage as negative and channel 1 has voltage as positive. Okay. What other thing I observe is both of these are actually settling to some value. This is at infinity. Here my V of infinity, V2 of infinity is settling to 0 volts. Here my V1 of infinity is settling to some voltage V. Okay. So across which element the steady state voltage goes to 0? It is the voltage across inductor. Correct. The voltage across inductor at steady state goes to 0. So obviously from this particular hint, if you have studied transient from us, right, this will be cakewalk. So you can directly say that yes, it is the voltage across inductor. So inductor is here. So obviously I cannot measure my probe cannot be here. Inductor is not here. This is resistor. Inductor is here. So the channel 2 has to have a probe at B and C because I am measuring the voltage across inductor. That is the hint, right? Voltage at infinity goes to 0, right? So for the channel 2, probe should be at B and C. Obviously I will read the options and I will cross verify this, but this is my first assumption, right? Hit and trial method. So that is for channel 2. Now for channel 1, I am saying it is like reaching some steady state voltage V. So what happens if some voltage is applied in a LR circuit? What happens? Steady state, the inductor voltage goes to 0. The current is some finite current V by R, whatever the voltage here is, and whole voltage is dropped across a resistor. Correct. So yes, this is the voltage across the resistor. Voltage across resistor, right? So obviously my channel 1 will be connected across the resistor, that is A and B. That is the voltage that I am measuring it, A and B. Okay. But can I cross verify this? So let's just check the options. Channel 1 AB and channel 2 is CA. CA, no, it should be BC, right? Or CB. Channel B option is telling AB and CB. So yeah, AB and CB is here, but this is other way around. So C is at the top and B is at the bottom. Why is it so? I will check this. Just hold on, let me read the other options. CB and AB. No, CB is not possible for channel A, channel 1. It is AB only, right? AB is for channel 1, not CB. So this is also gone. BA and BC. So BA and BC is again possible, right? BA and BC is also possible because this is across, BA is from here, right? So this is also possible. I am telling my positive probe is at the B point and negative probe is at the A point. Out of these two, which one shall I choose? Because I know most educators, they just directly solve and they just choose one option. They don't explain why the other option is not possible. I will explain here why the other option is not possible as well. So if I observe, I am observing at t equal to 0, my initial inductor voltage is going to negative. My initial inductor voltage is going to negative. Not inductor voltage, my probe voltage. My V channel 2 at 0 plus, right, is something negative. Now in these two configurations, which only one will be possible, okay, one will be positive and another one will be negative. So if I measure VCB, because C at the starting means it is the higher potential, that's the general convention. So VCB will be what? VCB, if you observe, C is here, right? So obviously inductor initially will be, it has no charge, so it will be open circuit. So whole potential will come across here. So whole potential will come across here. Basically I can say this is my B point, right? VBC will be equals to my V in, because there will be zero current here, no drop. So BVC will be equals to V in. Will be equals to V in, will be some positive voltage, as V in is positive, equals to V. But I am measuring VCV. So what will be VCV? VCV will just be the negative of this, right? It will be minus V. And exactly that is what I am observing in this oscilloscope as well, right? It is negative. It is not positive. It is lower than ground. It is some negative potential. So obviously my option B will be correct. We can cross verify this as well, right? If I choose option D, I am observing my positive probe is connected at B and negative is C, right? So I will directly measure BVC, which is some positive voltage, which is exactly incorrect because channel 2 is telling me at t equal to 0 plus, that is around here, I am getting some negative voltage, which is not possible, right? So just hold on, I will check if everything is recording. Yeah, everything is recording here. Okay, so which is not possible basically. So that's why we will rule out this option D. If you want to cross verify with the channel 1 as well, you can cross verify. So it is telling me channel 1 has a BA connected. So B is here and A is here, right? So actually with channel A, right, you cannot tell with t equal to 0 plus, because at t equal to 0 plus the current is 0, so drop across the VR will be 0 only. So for this case and for this case, both case I will get 0 only, because negative of 0 or positive of 0, it's almost 0. Okay, but what about infinity? If I go at infinity, I am observing the channel 2, this is plus of infinity, this is plus V, right? Plus V, some positive voltage. Okay, not channel 2, sorry, channel 1. So in which case at infinity this becomes short circuit, right? If this is short circuit, this is grounded, so C and B are same, so it will be zero potential and this will be some positive potential, right? So obviously this point will be if I choose BA, VBA will be what? You can simply apply the KVL. The circuit will become something like this. I will just draw the circuit. Now here they have, even though they have given the square waveform, my assumption is my inductor, the time constant is very very low, so it will be charged. The inductor will be totally energized before this waveform goes to 0. Okay, that is my assumption. And here also it is showing some exponential response, it is not showing some other response, so I'll assume it to be like that only. So not this. If I just draw the circuit, this is V, this is R, my inductor has been short circuited. So my inductor has been short circuited, this is R, correct? So this is my B point, this is my C, this is my A point. So if I measure, can you identify what is VVC here? Not VVC, sorry, VBA. It will be minus V, right? You can simply write the KVL and all those things. It will be simply minus V. But my VAB will be what? It will be plus V. So which one is matching? Is VBA matching or VAB? Obviously VAB is matching, right? At infinity. This is at t equals to infinity. So obviously my VAB is matching. So obviously the probes will be connected between A and B and not B and A. Okay, so that's why I told you option B will be correct and not D. Okay, most educators will not explain this part. Okay, so you have to understand why the other options are not true. What is the reason behind that? Okay, this was a very good question that came on GATE 2007. Okay, so the response, exponential. If you are not able to understand how am I writing the response and all those things, please, you have to go and watch the transient. I will not explain it here. Okay, because we have just taught transient very well. Okay, I don't want to repeat that same process. Let's do this question. The two inputs of a CRO are fed with two stationary periodic signals in XY mode. The screen shows a figure which changes from ellipse to circle and back to ellipse, with its major axis changing orientation slowly and repeatedly. So what is happening? My CRO, right? CRO is showing that I have a moving ellipse. So let's take what is the situation. Situation is something like this, right? That with this and this. So at starting it was like this, major axis was here, then again it become a circle, then again it become like this, right? So obviously the ellipse is also changing, the Lissajous pattern across the CRO is also changing. So obviously the waveforms are also changing actually. So what is happening? The following inference can be made. So this is the situation. Okay, I've drawn it. Please pause the video, try to read the options and try to see which option is the correct one. The signals are not sinusoidal. Can you say that? No, you cannot definitely say signals can be sinusoidal. What is happening here is basically the phase difference, right? Phase difference is changing, because as we've changed the phase difference, the ellipse, like the ellipse, right, in which axis it is present, that also changes. For phase, this is for phase difference equals to 90 or 270, correct? This one was for phi less than 90 and this one was for phi and between 180 actually, and phi greater than 270, and this one is for phi between this is for phi greater than 90 and less than 270. Okay, so the phi, I can see phi is varying, right? So what is happening? The following inference can be made. The signals are not sinusoidal. I cannot comment. The amplitudes are very close but not equal. No, amplitude has to be equal in case of ellipse, right? The amplitude should be equal actually if they are forming a ellipse-like pattern. The signals are sinusoid with their frequencies very close but not equal. If the frequencies are very close and not equal, right, we'll form a loop. Okay, we'll form loops and there will be some cut across intersections of the signals, but there is no intersection here. So this is not true, because we'll need a loop here. For ellipse and circle, the amplitudes are generally equal. So amplitude will be equal for ellipse and circle. Signals are sinusoidal, not sinusoidal. I cannot comment about that. Don't know. They can be, they cannot be as well. But if I am getting ellipse or circle, right, I have proved it to you that they will be sinusoidal. Not prove actually. I've told that they have to be sinusoidal. So I'm getting ellipse or circle. So it is not like they will be sinusoidal. That is for sure. There is a constant but small phase difference between the signals. Okay, there is a constant but small phase difference between the signals. So what I can say is that this is looking like correct. Why? Because let's say my phase difference, like actual phase difference is phi, is almost nearly equals to 90 degrees. Okay, but sometimes my phi becomes 89 and sometimes my phi becomes 91. So I know at 91 degrees it will be this diagram in the CR, right? Because it is phi is greater than 90. At 89 degrees this will be the diagram, and at 90 degrees it will be a complete circle. So obviously it is changing between circle to ellipse in first and second quadrant. So obviously this is the situation here. Whatever it is explaining is true actually. Thus there is a small phase difference between the signals. So option D will be correct. There is a small phase difference between the signals. Okay. So let's read this question. This is again like pretty simple question only. Here what they are asking: in an oscilloscope screen, linear sweep is applied where? What is linear sweep? Linear means this, right? And we apply some waveform like this, right? What do we apply? We apply a sawtooth waveform. Where do we apply sawtooth waveform? In the time axis, in the x-axis, horizontal axis. Why? To replicate the time, right? To replicate the time. So this is just a theoretical question. They ask theoretical questions as well. That's why theory is also important. Now let's do this question. Two signals S1 and S2 are shown. They are applied in Y and X deflection plates of an oscilloscope. So what will be the Y? What will be the displayed? What will the waveform displayed on the screen? So I can observe my X, right, is only varies between two values. That is 1 and this is actually minus 1. They haven't mentioned this is minus 1. So my X actually only varies between two values, 1 and minus 1. Correct. So my X axis, right, it can only take in two values, 1 or minus 1. So yeah, this is again not possible because it is telling my X can take all values between 1 and minus 1. It is also again my X can be here as well, X can be here. No, not possible. Here also it is telling my X can be here, X can be here. No, only this option is satisfying that my X can be here. But let's read the question further, because X can be either 1 or minus 1. That is the only case. And my Y is actually varying between 1 to minus 1, but my Y can take in all values between minus 1. So X is actually discrete. X can either be 1 or minus 1. But my Y can be in between any. Y is continuous. Y can take any value between 1 and minus 1. It can take any values. Okay. So Y axis is continuous, but X axis should not be. It will either be at 1 or minus 1. So just let's take few examples. At time t equals to 0, what is X? X is 0. Sorry, X is 1 and Y is 0. So at I'm here, Y 0 and X 0. I'm here, right? At t equals to, let's say, this some small t by 2. My Y is peak 1, and at this particular period, right? Actually, this is my whole time period. Both are time match. So this will be t by 2. Correct? T by 2. There is a transition between here to here. Just before this, t by 2 minus. This is my t by 2, right? This is also my t by 2 actually. Now this will be t by 4. This is the half of this. So this will be t by 4, correct? This is t by 4. The peak where the peak of Y is happening, it is t by 4. So at t by 4, this is not t by 2, this is t by 4. At t by 4, Y is 1 and X is 1. So here Y is 1 and X is 1. And at t by just before t by 2, Y is just equals to 0 and X is almost equals to 1. So it will be somewhere around here, and it will be somewhere around here only. X is 1 and Y is 0. And again at t by 2 plus, X is 0 and Y is 1. It will not be this waveform. Why it will not be this waveform? Because my X cannot lie here, right? X can only take two values. But this point is telling me that X is equal to some value between 0 and 1. No, it is not possible. X can only take discrete two values. Can only take this can take infinite values. So Y can take infinite values, but X can only take two values. This 1 and minus 1. Okay. So for this particular question, option A will be correct. Just you have to identify how is my Y and X varying. Okay. So let's do this question. The slope and level detector circuit in a CRO has a delay of 100 Newton second. The start-stop sweep generator has a response time of 50 nanosecond. In order to display the delay correctly, a delay line should be inserted. So, what is this telling? So, the start-stop sweep generator has a response time of 50 nanosecond, and CRO slope and detector circuit has a delay of 100 nanoseconds. Why is there a delay? What is the start-stop sweep generator? Sweep. Whenever there's a sweep generator, right? That means it is a time. It is talking about the time generator. Time generator. Or the delay in the horizontal axis. This is in the horizontal axis, right? as I have mentioned previously, the CRO may have some delay associated with it. What is the delay? So here if I observe that in the horizontal circuit I have a time ramp response, right, and that has some delay. This amplifier has some delay associated. Why? Because it is the rise time fall time delay, right? It cannot abruptly rise or fall. So obviously due to that there will be some delay, and that delay is provided here. So CRO, slope, level and detector. Slope and level detector means like somewhere here, like they have some configuration. So slope and level detector has some delay of 100 nano. So total delay in the horizontal axis will be 100 nano plus the delay in the sweep generator. So somewhere here or time based generator, right? Time based generator delay will be this 50 nano, and the slope level detector delay will be here at the triggering circuit. Correct. So this delay is 100 nano and this delay is 50 nano. So total delay is 150 nano, right? So this will be equals to 150 nanoseconds. So horizontal delay. Now obviously I have to synchronize it. So horizontal time axis has a delay of 150 nano. So obviously the y-axis, corresponding y-axis should also have a 150 nanosecond of delay to synchronize it. If I don't synchronize it, then how like can the waveform be shown? Like let's say time has a delay of 150 nanoseconds. So if this is y equals to sine omega t, and this has a delay of 150 nanoseconds, right? So here my time is actually equals to t plus 150. Correct. So at t equals to 0, this value will be 0, and at t equals here 0, it is telling me I am at 150 nanoseconds. So at 150 nanoseconds, I will have the value of y as 0, which is not correct. Because at 150 nanoseconds, if I put t equals to 150 nanoseconds, it will be some other value that will not be equal to 0. My y will not be equal to 0. It will be some other value. So obviously I am making some mistake over here, right? So to recover that mistake, what I'll do, I will delay this line also by 150 nanoseconds. To synchronize, just hold on. Okay. इसमें खत्म कर दूंगा भाई, तुझे क्या लगता है? I'll write down, just hold on, I'll write down, to synchronize x and y axis, we have to add a delay in the vertical axis. We have to add an additional delay. Add an additional delay. Okay, so that is the case over here. So that's why, like, first I wanted to explain the question, then I will read the question obviously. Then what are they asking? In order to display correctly a delay line of what? Delay line here. So that's why if you ever see the block diagram of a CRO, there will be delay line in the vertical axis, just to synchronize with the time based generator, right? That's the purpose of this delay line. That's it. So a 150 nanosecond has to be inserted in the Y channel. 150 nanosecond has to be inserted in the X channel. So X channel already has 150 nanosecond of delay. Why will I add another 150 nanosecond of delay on the X channel? No. Okay. 150 nanosecond has to be inserted in both X and Y. X already has 150 nanosecond of delay. Why will I add another extra delay further? Doesn't make any sense. 100 nanosecond has to be inserted in both X and Y. This 100, why does it come from? No. Obviously option A is correct. That's why I skipped the option A. So 150 nanosecond has to be inserted in the channel Y to synchronize, to perfectly synchronize with the channel X, right? Because X, this is the delay in the horizontal axis, right? To synchronize this with the vertical axis, I have to add another extra delay. Okay, so like this theoretical question you should know basically. So let's solve another question. A stationary closed Lissajous pattern on an oscilloscope has horizontal tangencies and 2 vertical tangencies for a horizontal input, okay, with frequency 3 kilohertz. So my FH is equals to 3 kilohertz, and they are asking the vertical input frequency. So I know FV by FH, like this is simple formula based, right? So this will be NH the opposite upon NV. So this is equal, what is NH? So what will be my FV then? FV will be simply equals to FH, that is 3 kilohertz into NH. NH is the horizontal tangencies divided by the vertical tangencies 3 by 2. So this will be 9 by 2, that is 4.5 kilohertz. Okay, so it's just simple formula based question. This is nothing, right? This question was nothing. The questions that we have solved are much more difficult. Okay, so option D is correct. So now we'll study about digital voltmeters. So what are digital meters? Basically, mainly in digital meter, right, we'll mainly be focusing on multimeters. So in digital meters, the primary measurable quantity is DC quantity. Actually, we measure a DC voltage, but we convert it. We have a switch that converts everything into DC voltage, and then with the help of that converter, we can measure anything. All other parameters such as AC voltage, current, resistance are first converted into DC voltage. This analog voltage is then converted to a digital signal using analog to digital converter, also known as ADC. The digital output is then processed and displayed on a 7-segment display. If you guys know 7-segment in display, what it means is that I have 7 digits. Like 7 segments means each digit, right, has 7 segments. So if you observe 1, 2, 3, 4, 5, 6, 7. So this is known as the 7-segment display. Each digit has 7 segments. So either one of them will be like a combination of them will be on to denote a particular digit from 0 to 9, right? Any combination. So that is what a 7-segment display means. Not that important in our case. Mainly the numericals are important. Mainly this ADC portion, right? We have a ADC that converts this DC voltage into AC. This analog into digital. Okay. So with the help of that, all everything is digitized. That's why the name digital meter. Okay. So we can measure anything in multimeter. If you have observed in lab, right, there are multiple like knobs here. If you observe, there is some like many knobs here for measuring ohms, voltage, all these things are here. Okay, I don't want to go into it, but if you have observed in lab, there are many knobs. You can rotate this like knob anywhere and it will measure that quantity. So what it does is basically it like has a switch. This is a switch, right? It can measure anything. Some DC voltage, some DC current, some AC current, some AC voltage, and each of the switches, right, each of those paths have different type of converters. This is calibrated attenuator, this is current to voltage converter, again current to voltage converter for DC, and this is calibrated attenuator. So we have these types of converter. Then it goes through, like for AC it goes through rectifier circuit, and then it goes to the ADC and to digital converter, or here it directly goes to the ADC as it is a DC signal itself, right? So then finally after going through the ADC, it goes to the this display, 7-segment display, and it displays whatever the value we have. Okay, we have all those calibrations and all those things are present in the meter itself. So that is the working principle. Basically, we don't need to go too much into this. Just this much you have to understand. This much you have to know. That's it, right? This block diagram. So this ADC, right? If you have studied digital electronics, it can be of multiple types. Dual soap ADC, successful approximation type ADC. Okay, then counter ADC and flash ADC. Now I will not go through the formulas, like there is some conversion time of each ADC, right? This have been taught in digital. You can go and watch the digital lectures, there it has been taught. We don't have time to prove all this. So for dual soap ADC, the conversion time is 2 into n plus 1 into t clock. This is the maximum, and the minimum conversion time is 2 raised to power n t times t clock. So what is n? N is the number of bits. So whatever bits I have, okay, in the 7-segment display, that will be the n. So what do you mean by bits? That also I'll explain, don't worry. Okay, bit meaning how many different combinations I have. Like this is like this ADC, right, can have like it has analog input and digital output, correct? So how many bits does have the digital output? Because digitally I can only denote in zeros and ones. So this can be the 0 to 1, 0 to 1, 0 to 1, right? So that is what I am talking about. This bits. How many bits I have? Like 1, 2, 3, 4. Total 4 bits. Okay. So that's why here n will be 4. So just like that. So this is the conversion time. Then conversion of time for SAR is n times t clock. Counter type, it is 2 raised to power n to t clock, and minimum is 0. It depends like from which we start, from which number. If you start from 0, it will be 0 only. If you start from like let's say the maximum value of the range, it will take this much amount of time to convert. And this is the conversion time for flash ADC. It is constant because I have like comparators in parallel that are running simultaneously, right? That's why it is constant, it is fixed. Okay, this is also fixed. Okay, so this is my conversion time. This you should remember. If you are not able to understand this, you have to go and study the digital electronics converters, data converters. There you will understand this. Okay, so yeah, that's basically what you do. These are the few things that you need to remember, and few formulas. The first one is resolution. What do you mean by resolution? Resolution is the smallest value of the input that can be measured by the meter. But do remember, this is actually unitless, and this is a global parameter. What do you mean by global parameter? It mainly depends on the how many digits I can display, right? So it can be of any unit. The digit, it can be anything, right? So let me give you an example. So if I have 3-digit display, right? So this can display between 0 to 9, this can display between 0 to 9, this can display between 0 to 9. Okay, so what will be the resolution? Resolution is the smallest value of the input. So here, what I can do, I can place the point, right? This point can be here, here, or here, correct? So tell me okay, if you are like in your head only, you try to answer, why should I place this point so that I can get the minimum possible value? I can place this point here, right? If I place this point here, what will I get? This will be 0, like this will be anyways point, this will be 0, 0, and this will be 1. So this is the minimum possible value that I can get out of this meter if the point is somewhere here, right? So this is a global parameter because this is mainly dependent on the digits, okay, not dependent on some value or something. So here some voltage, current, not that. It's just displaying the unit. What is the smallest possible unit that I can display here? 0.01, right? Obviously 0.00 is the smallest, but I'm talking about the smallest possible unit, that like this distance, right? This is the distance that I can detect, smallest possible distance of the digits. This distance is what I'm talking about, correct? So what is this actually? This is actually equals to 10 raised to power minus 3. So there can be another way to write this as well. What is another way? This has 10 combinations, this has 10 combinations, and this has 10 combinations. So this will be from 10 times 10 times 10. And if I take the inverse of this, 10 raised to power whole cube, this will give me the same result, right? That is 10 raised to minus 3. So we developed a formula, but the basic fundamental thing I hope you can understand, that the minimum smallest change that I can detect, right, in units, not in like voltage or current, not in some exact measurement, not in the measurement, in terms of the units of the digits of the meter. Okay, so that is the formula for this. N is the number of full digits. Full digits meaning this 0 to 9, right? I can like this device can show any number between 0 to 9. So if a number shows anything between 0 to 9, if a digit, like if a device on a particular place, it can show any number between 0 to 9, it is known as a full digit. Okay, what is half digit? I will come to in the next few slides. I will come to that. Sensitivity is equals to resolution times range. It is similar concept as resolution only, but sensitivity is the measured quantities. Sensitivity defines the ability of the multimeter to respond to small changes in the input level. It is defined with respect to the input level. So yes, my device can detect this much amount of change, right? But this is unitless. What if now I give a unit to this? So what if I tell you, thus currently I have a range of 5 volts. 5 volts. If I have a range of 5 volts, what is the minimum change it can detect? Actually, it can detect 0.05 volts. Why? Because if you observe, sensitivity will be full scale divided by total number of divisions, right? So that's what each division will represent. So I can directly say, what is the full scale? Full scale is 5 volts. And what is the number of divisions? So how many divisions I can have? 10 here, 10 here, and 10 here. Total 10 raised to power 3. So this will become 10 cube. So my answer will come out to be 0.005. Okay, so each small change, right? Each small change in the digit represents as 0.05 volts. It is not equal to 0.001. Okay, that is unitless. Okay, that is unitless. That is the global parameter of the multimeter. But my full scale is 5 volts. So it is like, what is the full scale here? What is the full scale? Full scale will be this, right? 999. Correct. And what is the smallest value? No, smallest value is 0.001. Correct. So like, how many different states I can have? How many different states I can have? I can have total 1000 states. Okay, 1000 states. So that's why each small change, right? Each digit, each small change here represents a total of 0.5 millivolts. So I can measure in steps of this is 5 millivolts, right? I can measure in steps of 5 millivolts. Okay, so I hope you understood this point, what each step means. This is the smallest step. Resolution, we can understand it like smallest step. And this is the smallest detectable output, okay, of the input measured quantity. Okay, I hope you understand the difference. We will do few examples. Obviously from here you will understand. We have a 4-digit digital multimeter used as a 100 volt range. So I have a 4-digit digital multimeter, right? So this is here. This digit can go from 0 to 9. This digit can go from 0 to 9. This digit can go from 0 to 9. Correct. So here the smallest, what is the sensitivity? First I will find out the resolution. What will be the resolution? Resolution will simply be 0001, and if I place a point here, that will be my resolution, right? The minimum detectable input. Okay, so it is 0.001. I can directly say it is 0.0001, or I can directly say here 10 raised to power minus 4 as well. This can be written as 10 raised to power 4, that is number of full digits, right? Divided by 10 raised to power number of full digits. Same formula. Now what about the sensitivity? What is the minimum detectable input? Sensitivity, again I will use this simple formula, is what? This formula, right? Number of full scale by total number of divisions, or full scale into resolution basically. So total number of divisions is basically 10 raised to power 4, correct? And full scale is, again they have mentioned 100 volt range. 100 volt range divided by total division, that is 10 raised to power 4. This will be equals to 10 raised to power minus 2. Okay. So like, how it happens basically? How it happens? My voltmeter range, my multimeter range should be from 0 to 100, right? Now at the starting you said that I can place the point here. But if I want to measure from 0 to 100, can I place the point here? No, I cannot place the point here. I have to place the point somewhere around here. Okay. So what is the maximum? Maximum will be 99. And what is the minimum? Minimum point will be fixed, right? This point I cannot change. Once I fix the range, I cannot change this point. Okay. So minimum will be what? Minimum will be 0.01. So from here can you say me what is the minimum detectable output? That is 0.01 volts, right? Which is exactly what is the same written over here. So this is the method 1, using the formula. Or if you are not able to understand using the formula, you can use the visualization. So my meter has to measure the range from 0 to 100. So my point has to be here. Point is fixed. Position of point is fixed. Previously resolution is the minimum that the meter can display. So point I can place it here. Okay, that is the minimum that the meter can display. But I want to measure from 0 to 100. To measure from 0 to 100, my point has to be here, because at least I have to measure this maximum voltage, right? So that's why point will be here. So from this I can directly say the minimum sensitivity detectable change will be 0.01 volts. Visualization you can do. You can use the formula. Either way works. Now there is another concept of overranging. So overranging refers to the feature in the digital instruments where an extra fractional digit extends the range of the measurement. Let's take, like that's what I told, right? Full digit means it can go from 0 to 9. But if I am using overranging, right, then the value will not go from 0 to 9, it will go to some other value. I will show you. A 3.5 digit display includes an additional fractional digit, allowing the range to exceed than the usual limit. So what does a 3.5 digit display? So 3 digits will be full, right? 3 digits will be full. Okay, this will go from 0 to 9, this will go from 0 to 9, and this will go from 0 to 9. But I will have a half digit that will go from 0 to 1. Half, it can only take 2 states. That's why half. 1 by 2. 1 by 2. Okay, it will be the 0 and 1. So previously what I was able to measure, previously the maximum voltage, right? If point is not, like point is here, point is not here, it was 999, let's say volts something, right? Now what I will be able to measure, I will be able to measure 199. So range has been doubled. That's why half. That's why simply half. Range has been doubled. Okay. So this is the nomenclature for 3.5 digit display. So this is what is written over here. For, like here, it's the same thing is written, right? Maximum count becomes 199, allowing up to 2000 states. Previously it was only allowing up to 1000 states. But there is another like similar concept only. Display as 3 and 3 by 4 of digit. What does 3 by 4 of digit means? It can measure 4 states. So the 3/4 digit, right? 3/4 digits means 0, 1, 2, 3. Okay, that is the state basically. 0, 1, 2, 3 states. Okay, so depending on the complexity and versatility, we will use any of this 3 by 4 digits or half digit, anything you can use. Okay, so 3.5 digit instrument is used to measure 10 volt. So find the sensitivity. So now what will be the sensitivity? It is used to measure a range of 10 volts. So now if I observe, you can do using two methods. One is the resolution method, another one is the simple visualization. So method 1 is the formula. Now what will be my resolution? So if I observe, my resolution now will not be simply this, right? I have 3 digits. Okay, now don't confuse that. You will draw the 4 digits here and you will take the range, everything as 0 to 9, 0 to 9, 0 to 9, and then you will find the resolution. It will be 10 raised to power minus 4, and then you will write the sensitivity will be 10 into 10 raised to power minus 4. It will be 10 raised to power minus 3, which will be obviously wrong. Okay, you cannot do it like that. So why? Because this final digit, right, was not supposed to be a full digit. This final digit was not supposed to be a full digit. It was a half digit. Okay, so here this is a half digit. So it can either take 0 or 1. This will be from 0 to 9. This will be from 0 to 9. And this will be from 0 to 9. Okay. So what I can say is that now what is the resolution? Equals to, just hold on, I will check if everything is recording or not. Yeah, everything is recording. Equals to, now how many digits I have here? These are 2, right? So I can represent 2. So 2 into this can represent 10, 10, 10. So total combinations will be 2 times 10 into 10 into 10. So this is the resolution. What will be the sensitivity? It will be simply range times the resolution, right? What is the range? Is 10 volts. So 10 into 1 divided by 2 into 10 cube. So it will be 1 divided by 2 into 10 raised to power minus 2. It will be 5 millivolts. Okay, so here I can totally show 5 millivolts in half digit, right? So now if I solve it using the formula, I can be wrong. Okay, why I can be wrong? I will show you why I can be wrong. Okay, so that's why sometimes basics is very, very important. So if I solve it using method 2, method 1 is this. Okay, I already told you method 2 is basics, right? So here are my 4 digits and they have told me that I want to measure 10 volts. Okay, and this is a half digit. This is a half digit, right? So this can only go from 0 to 1. correct? So here I have this can go from 0 to 9, this can go from 0 to 9, this can go from 0 to 9. Now I want to measure 10 volts. If I want to measure 10 volts maximum, this can be 1 0 0 0, correct? And the points can be here, right? Obviously my maximum value should be 10 volts, correct? Now I can do it like this as well. This will be like, this is 0 9.99, so this is also 10 volts. So either way works. So now out of this, what is the total resolution? So what can I measure in minimum? This will be like this is, what is the minimum value of this? 0.01. okay, this is the amount of voltage, which is this is 0.01 volts, right? 0.01 volts. This is the minimum voltage that the multimeter can detect, basically. So minimum voltage will be 0.01 volts. 0.01 volts. This is the sensitivity. Sensitivity is the minimum detectable volts. So this is the 0.01 volt, that is 10 millivolts. Now you might say, sir, what if why is it 10 millivolts? So what we could have done is, actually we are not using the extra range. We are not using the extra range. So what we could have done is, if we would have measured 20 volts, right? If we would have measured 20 volts, then it would have been beneficial, because for 20 volts, this maximum value, this can go to 9, and this can be 9. Okay, so this is the maximum range for 20 volts, correct? So in 20 volts, my resolution, I can say from sensitivity is 0.01 volts. So even if the range increases, I can still, the sensitivity will be same. But for 10 volts, I'm not using that extra range. The sensitivity is just lower, so it is just getting wasted. The extra range is just getting wasted. So actually, what went wrong here? This extra division by 2 actually went wrong. Okay, why? Because this was for 20 volts. Okay, that's why. So that's why I will not recommend you always solve using the formula. You can solve using this method, right? Just by understanding what is the minimum range, just write down the things, just write down the digits, the maximum and the minimum, and from there you can understand what is your sensitivity. So first you write down the maximum, arrange the point, and write maximum. Okay, and then you write minimum. This is the first step, and second step is write minimum. Okay, so that's why you have to be very, very careful in this type of questions. So let's do another similar question like this. This time we will actually utilize the full range. A 3 and 3/4 digit digital multimeter is used in 40 volt range. Find the sensitivity. So this one will be simpler because I have 4 digits, right? But the fourth digit, this is a 3/4 digit. That means it can only take values between 0 to 3. So the maximum it can go is 3, right? 3. This can go from 0 to 9. This can go from 0 to 9. This also can go from 0 to 9. 9. Why should I place the point? Point I should place here, right? If I place it here, I will get my maximum value. So my maximum value is 40. Now I will write the minimum value. The minimum value will be 0.01. Okay, so this is my sensitivity. So no need to use any formulas. With the formulas you can directly do. Okay, so write the maximum value, then you then you place the point, and then you write the minimum value, and according to that you will get your sensitivity. So this is the process that you can follow basically. There is another concept known as error in digital multimeter. So error in digital multimeter can be due to two main reasons. One is the error in the reading. So whatever you're reading, there is an error in that itself. So that percentage error in the reading times the reading itself will give you the reading error, correct? And this is known as the reading error. Okay. Known as the reading error. And what will happen is your digital multimeter, let's say your digital multimeter, actually what it should have shown is 0020, but instead of showing 0020, it is showing 0021. There is some count error. Okay, it is showing 0021. So that is the internal circuitry that has some error. Due to that, there will be some count error. Generally the LSB, right, this will be have some error. So that will be the number of counts by which I have error and what individual count actually represent. Basically this is as the sensitivity, right? This thing is range of the meter, basically the sensitivity. So this is also known as the count error. By how many counts it is missing. Okay, so like I can show you example. Let's say I have a 3.5 digit digital multimeter, DVM, and I'm measuring a range of 20 volts. Okay, so again this first digit can go from 0 to 1. This will go from 0 to 9, 0 to 9, 0 to 9. So this will be 1, 9, 9, 9. Okay, so I can say like the maximum is 19 volts, let's say 20 volts basically. So what is the error here? So if we assume here some error, right, let's say 3% is the reading error. So I'm reading, let's say I'm reading 10 volts. Okay, so if I'm reading 10 volts, that is measured, we measured, and I have an error of 3% reading error due to probes and all those things. Okay, and I have count error as 2. Count error as 2. So what is the actual total error, right? So total error will be 10 into the reading error percentage 300 plus number of counts by which I was misplaced. Let's say I was supposed to give something like this, right? This digital meter was supposed to show like 10 volts. So it was supposed to show this, but it is either showing 9.98 or 10.02. So there is a count error of 2, right? 2. Okay, plus minus 2. So either way you can directly write from here itself, it is 0.02 volts, or you can use the formula. What is the formula? Formula is this one, that is full where did it go? Full scale divided by range of the meter. So what is the full scale? Full scale is simply you can directly write the sensitivity here. Sensitivity is 0.01. So it will be this will be 0.3 plus 0.02. So the error will be 0.32. So this will be error basically. Okay, so yeah, I hope you understood this particular point. Here instead of writing full scale by range of the meter, right, better you write it sensitivity. That would be better. Without remembering another new formula, you write it sensitivity. So because each count represent the minimum value that I am like that the input like that it can show as the output, right? So obviously if I multiply the number of counts that I am differing from the actual value into the sensitivity, I will get the total error, right, in volts. This in the actual units. This in the actual units. This has units, right? Unit is of the measured quantity. Unit is same as the measured quantity. So like gave a question on this, like pretty simple question. So it 4.5 digit digital multimeter has the error specification of 0.2% of reading plus 10 counts. So it gives error of 10 counts. It can either be plus minus 10, right? Plus minus 10. basically. If a DC voltage of 100 volt is read on its 200 volt full scale, so like what is its full scale? If I want to measure separately, I have 4 digits, right? I have 4 digits, and the first digit can either go from 0 to 1, this can go from 0 to 9, this also 0 to 9, this also 0 to 9, and this also 0 to 9. So this can, the maximum is 1, and this can be 9, 9, 9, and 9. Where shall I place the point? It is telling me 200 volt full scale. So if I place the point here, I will be able to measure 200 volts. So I'll place my point here. The maximum error that can be expected in the reading. The maximum error that can be expected in the reading. So what is the maximum error? Basically, I have 0.2% reading error. So how much I am reading? 100 volts. So error will be 100 volts into 0.2% because I have 0.2% of reading error, plus the count error, right? 100 counts, I have error as count, but what does each count represent? So each count represents 0. If I write down the minimum value, right, it is 0.01. Each count, this is the value of the each count or the sensitivity. So each count represents 0.01 multiplied by this. Okay, so this is equals to how much? 0.2 plus 0.1, that is 0.3. But what are they asking? They are asking in percentage. Percentage with respect to the what? With respect to the reading. In the reading. Percentage with respect to the reading. Okay. So error percentage will be error in absolute terms divided by the reading, basically. Right? Divided by the ideal reading. Ideally, what it should have shown? It should have shown 100 volts, right? Okay, so error, how much in absolute term? This is 0.3 volts, right? 0.3 volts. This is 0.3 divided by ideal reading is 100 volts, and obviously I have to multiply by percentage, right? Because I have to multiply by percentage as well to make it in percentage terms into 100. So this will be 0.3 percentage. So everything is same because the reading value is also 100. So 100 gets cancelled. So there are a few advantages of digital multimeter. What are those? It has high input impedance. It minimizes circuit loading, reduce loading effect, digital displays, more like we don't have to look at the pointer and see where it is actually pointing to which value, because it shows a digital output, right? So we can directly see that it is showing 19 volts. I don't have to have any observational errors. Better accuracy, portable. So digital has very good advantages that you should know. This is like this you should know for ESC. Okay, GATE generally doesn't ask these type of things. Now let's solve few questions on digital multimeter. So this is the first question. This is actually mainly a question of ADC. Okay, this is not a question of digital multimeter. They have told us that we have a temperature range from -40 to 50. So what is the total range? Total range will be 55 minus of -40 degrees centigrade. It will be 95 degrees centigrade with a resolution of 0.1. The minimum number of ADC bits. So this is basically a ADC question. This is actually not a simple digital multimeter question. Actually, I had to take it because ADC was here only. So like there is a formula, if you remember, or you already have studied, that your resolution was equals to range upon the number of steps. This represents the number of steps. So obviously like I don't need to write this n here is the number of bits of the ADC, right? Number of bits of ADC to have those many steps. So directly from here I know range, I know resolution. What is the resolution? 0.1 degree centigrade. So I can directly write that 2 raised to power n is equals to 950. So I have to choose, like n will be the upper bound of log base 2 950. So this will be equals to what? 950 log base 2 will be almost like 10 only. Upper bound is 10. We'll need minimum of 10 bits to represent 950 different states, right? 950 different steps. So obviously the answer will be 10 bits. So this is actually a digital question, but as like few measurement components were there, that's why I have to explain this. Now let's do this question. So we have a 3.5 digit digital multimeter that has the following error specification: 1% of the reading and 4 counts. If a DC voltage of 50 is measured of a 200 volt full scale, then the maximum possible error will be. So like we will find both in absolute and percentage terms. So first of all, I will write down the, like, draw the digit specification. This is 3.5. So this will be 0 to 1. This will be from 0 to 9, 0 to 9 and 0 to 9. Okay. So this can like it measures total of 200 volts. So how can I measure total 200 volts? So my point should lie here. This will be 1999, right? Then only I will be able to measure total 200 volts. So from here I can directly say my resolution minimum value will be 0.1, correct? So what will be the total error in absolute terms? Error in absolute terms will be 100. Like I'm measuring 50 volts, right? Reading error 50 into 1% of that is 1 by 100 plus basically the count, how many counts I am making error, 4 maximum count, and into what is the value of the each count, that is 0.1, right? 0.1. So it will be 0.5 times 0.4, that is 0.9 volts. But if I want to quantify in percentage, it will be 0.9 divided by 50, that is a reading, into 100, right? Percentage. So this will be 1.8 percentage. Okay, this will be the error in percentage terms. Yeah, sorry for the interruption. Actually my recording got cut. Now we will discuss about the Q meters. So Q meter is nothing, just a series resonance circuit. We have a series resonance circuit and we measure the voltage across the resistor. Okay, not the resistor, sorry, like we'll just read this. A Q meter is an instrument used to measure the quality factor of inductive circuits. The quality factor Q, also known as the magnification factor, increases the efficiency of a coil in terms of energy loss. We already know. If you have studied network theory from me, all this has been explained. I will not explain here. Q meter operates on the principle of series resonance circuit, where the voltage across the inductor and capacitor is amplified by the factor of Q at resonance. So we measure two voltages. One is the voltage across the resistor and also the voltage across the C or L, anything, right? C or L, anything we'll measure. And by series resonance, if you know the condition of series resonance, that the voltage across the capacitor or the inductor, the magnitude of the voltage across the capacitor, I am not concerned about the phase, will be Q times the magnitude of this voltage, this E, right? So it will be Q times that. If I just find the ratio, I will get my quality factor. So that's it. That's the only thing that we do. So we use a series resonance concept, and with the help of that, we simply measure the voltage across the inductor and capacitor and also the resistor, and take the ratio, and from there I will be able to identify my quality factor. So these are few formulas. I hope you remember that there was a resonance formula which was omega naught equals to 1 by under root LC. Omega naught equals to 1 by under root LC. So from here you can identify the capacitance. If you know the resonance frequency of the particular circuit, you can find out the capacitance. If you know the capacitance, you can find out the inductance. Okay, either way, like either you this or this, one unknown will be there and other unknowns. Simple thing, right? Now if there is some self capacitance in the capacitor, right? If there is some self capacitance with the capacitor, what happens? That's like there is some parasitic capacitance or something. Due to that, there is some additional capacitance that can cause an error in the measurement. What we do is then we measure twice. The self capacitance and the testing capacitance of a coil or capacitor can be determined using the following methods. Adjust the capacitor to a higher value. Resonance is achieved by oscillation frequency. Okay, so what will happen? We will adjust our capacitance to measure the self capacitance of a capacitor. So let's say this capacitor is variable. Okay, this is a variable capacitor and I am varying the capacitance, but the self capacitance will be same because it is due to the environmental factors and all those things. So that will be same, that is CD, and it generally comes in parallel. So I will vary the C1 and then I will measure the resonant frequency, and will vary again it to some other value C2, and then again I will measure the resonant frequency. So everything else will be known, just this CD will be unknown, right? CD will be unknown. How will I determine? Just take the ratio of these two equations, and from there we can simply determine the CD. That's it. That's it, right? So why do we take it to some adjust the capacitor to some higher value? To neglect the effect of shunt capacitance. Okay. This is a theoretical point that you should know for ESC. To neglect the effect of shunt capacitance. Okay. So like this basic concept, just we are using the series resonance circuit. That's it. Only that much if you know, that much is enough. We'll do a few questions. A Q meter has an insertion resistance of 0.02 ohms and is used to measure the inductance of a coil. The resonance occurs at angular frequency omega naught equals to 10 raised to power 6 radian per second. Insertion resistance is 0.02 ohms. Q meter has its own resistance. Inductance of the coil is measured with a capacitance of 40 picofarad. What will be the inductance of the coil? This is just a simple formula, right? That's it. What is the formula? I don't care about the resistance because resonant frequency is independent of the resistance, right? Omega naught is equals to 1 by under root LC. So if you just simply solve this, you will get your L value. Just use that resonant frequency concept. That's it. L will be equals to 1 by omega naught square into C. So 1 by omega naught square is 10 raised to power 12 into C is 40 into 10 raised to power minus 12. So this will be like 10 cube divided by 40. So 4.25 millihenries. Okay. So 25 millihenries. So resonance, like this quality factor questions will be very, very simple and cakewalk for you guys. Let's do another question. A reading of 120 is obtained when a standard inductor was connected in the circuit. Okay. Like circuit of a Q meter. So Q standard inductor, when it is connected, it is 120. And the variable capacitor is adjusted to a value of 300 picofarad, 10 raised to power minus 12. A lossless capacitor of unknown value Cx is then connected in parallel with the variable capacitor, and the same reading was obtained when the variable capacitor was readjusted to 200 picofarad. So my C2 is 200 picofarad, but I am getting the same reading. Q is 120 and Q2 is also 120. Okay, nothing else has changed, right? Nothing else has changed. The value of Cx in picofarad. So obviously, if nothing else has changed, the capacitance, the final C dash, what is the final capacitance in the circuit? It is C2 plus Cx. The capacitance that has been connected should be same. If not everything else is same, this should also be same. So basically, C dash should be equals to C1, as Q1 is equals to Q2, as inductance hasn't changed, so everything will be same. So what is C dash? What is C1? C1 is 300 picofarad. C2 is 200 picofarad plus Cx. So Cx will simply be 100 picofarad. So answer will be 100 picofarad. So gate questions are this easy. Okay, they are this easy. Okay, so Q meter, there aren't many questions. Mostly questions will be simpler only. Q meter works on the principle of what? Mutual inductance? No. Self inductance? No. Series resonance? Yes. Parallel resonance? No. We use it for series resonance only. We multiply the voltage because it is easier for us to measure the voltage. So we'll use the concept of series resonance. That's it. So these were few questions. So Q meter, you can take it lightly. There are not many questions that come recently, but these are the few topics that we covered. We covered CRO, we covered digital multimeter, we covered Q meters, right? These three, like with the help of these three topics, you can expect at least 1 to 2 marks. So you have covered 1 to 2 marks within 4 hours. That's very good work for you. So that's it from this lecture, and in the next lecture we'll study about CT and PT. Thank you for watching, and we'll see you in the next lecture. Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we'll start a new topic, that is potential and current transformers. So we'll be continuing along with the CRO digital multimeter. We have studied that, and this is another miscellaneous topic, that is potential and current transformers. So first of all, we understand why we needed transformers. They are also called as instrument transformers. Why we actually require this type of transformers in the first place. Let us have an ammeter which can measure 1 amps of current. The maximum range of it, this ammeter, analog ammeter, is 1 amps. But actually I want to measure 1 kilo amps of current. How will I do it? So up until now what I have learned is we can actually place a shunt resistor which will carry the most of the current, and the 1 ampere current will flow through this, and the other current will flow through this RSH, and the load current will still be 1 kilo ampere. Okay, so up until now we have been doing this only. But what is the problem with this? So in here, what we used to do, we used to find the magnifying factor, right? Magnifying factor M equals to, just hold on, M equals to I, the I of the output divided by IM. Okay, so this needs to be what? This is 1 kilo amp divided by 1 amp equals to 1000. So I need a magnifying factor of 1000. So basically, if you remember in range extension chapter, there I derived a formula. No need to remember, you can solve using basic as well, but just I want to quickly explain this stuff. The formula was that was shunt resistance should be equals to R by M minus 1, RM by M minus 1. So so what will be my RM, or like what will be my RSH? RSH will almost be equivalent to RM by 1000, correct? So what is needed is we need a resistor which is 1000 times lower than the current shunt resistor, right? Like achieving this, getting this resistor right would be very difficult. Okay, so very difficult to build, just hold on, build this resistor, very difficult to build this resistor, right? And it also causes a loading effect. Obviously there is a resistor, obviously it will cause a loading effect. There will be some power dissipated, right? There will be some power dissipated in this resistor, and that power dissipated will cause the loading effect overall. So what we do to increase the range of a meter, we actually connect a transformer. What we could have done is we could have connected a series current transformer, and the current transformer, this transformer, the primary of it will take 1 kilo ampere current, the secondary will actually take a maximum of 1 amps. Okay, so and the current flowing through the ammeter is still 1, but the current flowing through the load is 1 kilo amp. And obviously I can say that how many turns ratio transformer I need. I know this formula, I primary upon I secondary is simply I secondary, like number of turns in the secondary divided by number of turns in the primary. So the ratio of these two peak values will be 1000, so this has to be 1000. So that what is the turns ratio? It is secondary has to have 1000 turns, right, over primary. So if I choose a transformer 1:1000, that should be able to do this. Okay, so this is much easier, right? What we do is, this is actually a step up transformer because the number of turns in the secondary is higher, voltage is stepping up, but current is stepping down. Okay, so we can do this, but there is one issue. What is the issue? This can only work in AC, cannot work in DC. Obviously transformer only works in AC, but there is very good advantage, right? It doesn't cause any loading effect. Here transformer is just converting the voltage, right? Power remains conserved in transformer. If you remember, power remains conserved, so we don't change the loading effect is not present here. Okay, so also we isolate the load with respect to the meter. That is also a good thing. So we can actually design a current transformer which will have turns ratio like this, which can actually measure this 1 kilo amp of current. And again, if you observe, like my primary current is proportional to the secondary current, so obviously meter current will be proportional to the input current. That relationship is still there. So these are a few points with respect to shunt multipliers and the CTPT. Okay, so shunt and multipliers lack electrical isolation, as I mentioned, between the load and the meter, but here we have electrical isolation. Current transformer provide electrical isolation. In high voltage applications, shunt multipliers have insulation challenges between the meter and the shunt multipliers, while CTPTs avoid this problem. If the meter is changed, a separate shunt or multiplier is required for each instrument, whereas CTPT can be used in any ammeter or voltmeter, right? Because actually this RSH, right? RSH is a function of the meter resistance. Okay, it is a function of meter resistance. But obviously I can observe that I know that this isn't function of meter resistance, because if I change the meter resistance will change, and so the shunt resistance. But if I change the meter range will change, and along with that this range also, by how much I can measure, that will only change. Okay, that's it. Okay, that's it. So this is independent here, independent of RM. This is not dependent of RM anyways. The relationship here, we have any RM? No, we don't have any RM. This is dependent of CT, turns ratio, that's it. But this is dependent on the RM. So that is another advantage of this CTPD. And like for high current and voltage measurement, power consumed by the shunt and multipliers is higher compared to CTs and PTs. Obviously, there will be some power consumed in the CTs as well. It is not ideally it should not consume any power. But nothing is ideal, right? Practically, transformers has some losses which you have studied, so it will cause some loss, but that loss will be very, very lower compared to the loss caused by the shunt and multipliers. That's why we use this CT and PT. That is the advantage. The current division between the meter and shunt can be inaccurate and frequency dependent, while the CTs and PTs offer more reliable performance. If you remember there, when I was deriving the expressions for multipliers, we saw, right, it can have a frequency dependency, but here in transformer it doesn't have any frequency dependency. It is almost frequency independent. There will be some variations, but it is much better than normal shunt multipliers. Okay, so basically instrument transformer, there are two words. One is transformer, one is instrument. So transformer is basically transformer, and instrument is used for measurement. Transformer, we step down. We can step down either current and voltage, because our measuring instrument can measure only 1 amps, but we want to measure 1 kiloamps on kiloamps. So what do? We step down the current on voltage. If we step down the current, it is known as the current transformer. So step down current, then it is known as the CT or the current transformer. That is what I can measure. Let's say load is passing 500 amps of current. I want to measure 5 amps. Okay, and if I'm stepping down voltage, it will be called as PT transformer or potential transformer. What I'm doing, I'm stepping down the voltage now. Known as the PT, that is some 20 kilovolt by 100 volts. Anything, it will depend on turns ratio. So like these are the requirements for instrument transformer, why we use it. Like a few things are written. Okay, the instrument scale is calibrated. Current transformer and potential also keen process extending the range of instrument. This already has been explained. You can read this features of the instrument, right? I'm not that interested in reading this. You can read this. But most important point is this basic principle. You have studied in machines that the voltage ratio will be equals to turns ratio will be equals to I2 by I1. Okay, so I can say my voltage is actually proportional to turns, number of turns. The higher the voltage, the higher number of turns on that particular side. Just one thing you should know is that if it is a PT, right? In PT, what do you do? We step down the voltage. So on the secondary side, voltage is proportional to the number of turns on that particular side. So secondary side will have lower voltage. So number of turns of the secondary will always be lower than number of turns in the primary. But in case of current transformers, we actually step down the current, which gives the opposite effect of the voltage, right? Because current is actually not directly proportional to the turns. Current is inversely proportional to the number of turns. So if I am stepping down the current, that means number of turns will increase. So my NP will be greater than NS. Sorry, not this. Sorry, NS will be greater than NP. NS will be greater than NP. So why? Because my IS will be less than, because I'm stepping down my current, secondary current, less than IP. That's why. And here my VS is less than VP. It is directly proportional. It is inversely proportional. So this is one thing that you need to keep in mind according to the number terms. It's a very simple relationship. Now there are a few terms known as burden. What is burden? The term burden refers to the impedance connected to the secondary winding of a current transformer or a potential transformer. So whatever impedance that will be connected on the secondary, that will be termed as burden. It can also refer to the volt ampere rating delivered to the load or to the burden. So like what is the volt ampere rating of the transformer? The rating of the transformer, that is also sometimes referred to as burden. For an ammeter, the resistance R is close to 0, meaning the power consumed is negligible. For a voltmeter, the resistance R is close to infinity, so the power consumption is again minimal. Why? Here in ammeter, we are mainly interested in measuring the current, right? So I square R is almost equal to 0. Here it is V square by R. Again, it is almost equal to 0. This is why they impose a light burden on the winding. So although, like, my assumption is they are almost infinity and 0, but in real life they are not, right? There is some power consumption. So that power consumption will be basically the burden, because that is causing a loading effect. I told you at the start that there is no loading effect, but practically there will be very small compared to the sun multiplier. It will be very small, but still there will be some loading effect. That loading effect is measured like this: either I square R or V square by RSH. Okay, what are the current flowing through and the meter resistance? That's it. So let's understand burden a bit more. So if I have a transformer, secondary of the transformer, with a meter resistance Zm, right, and I have a winding resistance as well, winding impedance as well, because you know the equivalent circuit of a transformer has its own winding resistance and leakage reactance, all those things. So that is equal to Zs. So what will be the secondary winding burden due to meter? It will be volt times meter. Due to meter, it will be what? It will be Vm. Everything is in RMS. It will be Vm times Im. So as it is connected in series, Im is Is only. It is Vm times Is. Okay, Vm times Is. And what is Is or Im equals to? Im equals to Vm by Zm basically. So it will be Vm square divided by the Zm. Don't confuse this with the maximum. This is just RMS. All these are in RMS, right? Generally we talk about RMS only. All the voltages are in RMS, voltage and currents. Now what is the total burden on the secondary winding? Total burden will be what? This voltage into the current, right? Is. So total burden will be Es into Is. Okay. So this will be equals to what? This will be equals to Es. What is Is basically? Is, either you can write in terms of Vm or you can write in terms of Es as well. It will be equals to, this will be equals to Es divided by magnitude of Zs plus Zm. So this is the like current in the secondary, right? Zs plus Zm. This is equals to Es whole square divided by Zs plus Zm. Okay, magnitude of Zs plus Zm. So this is really the secondary burden, total burden to the secondary winding. Okay, that's how we compute the burdens. Okay, I've just shown you an example. Now there are a few more terms. One term is transformation ratio. What is the transformation ratio? For a current transformer, the transformation ratio R is defined as primary winding current to secondary current winding. Secondary winding current. So you have to understand this, right? The transformation ratio will be primary winding current divided by the secondary winding current. What will be the nominal ratio? This will be rated primary winding current divided by rated secondary winding current. This, you might think that your R will always be equals to Kn, but it will not be always equal, but because there will be some error. That's why these are two terms are different. So you have to remember this term. Transformation ratio is the primary winding current divided by the secondary winding current. The nominal ratio is the rated primary winding current divided by the rated secondary winding current. Which one will be at the top? You can understand that R will always be greater than 1, right? R will always be greater than 1. And I know this, that I'm stepping down my current, right? For a CT, I'm stepping down my current. So obviously the top numerator should be higher than the denominator. So denominator should have the secondary current, because secondary is the where I am carrying the meter. So that will measure the lower value of the current, and the primary is carrying the load current that is very high, 1 kilo amp. Okay. So primary will be at the top numerator, and at the denominator secondary will be present. Okay. And difference between R and Kn I have explained. It is rated condition and it is for the normal general condition. Okay, we'll talk about the difference just in a bit. There is another term known as the turns ratio. The turns ratio is the number of turns of primary winding divided by the number of turns of secondary winding. This is the turns ratio. Okay, and this, okay, I'm at primary winding current. This side, this I think should be, because secondary should have more turns. This here, right, number of turns in the secondary winding to the number of turns in the primary winding. This should always be here. Yeah. So Kn will always be equals to N. because it is also talking about the rated condition, because number of tons is talking about the rated condition only in ideal condition. Ideally, number of tons by secondary to number of tons by primary should be equal to rated current in the primary divided by rated current in the secondary. But it actually doesn't always happen. There is some error in this R, right? It is not always equal. So there is some error. So that is the only thing that I want to take. Okay, actually sometimes what we do is the turns ratio, from what I remember. I also don't remember this usually these terms, because don't worry, gate will give you these terms. Or gate will most probably give you these terms. Kn will be equals to 1 by n. From what I remember, it was supposed to be 1 by n. Yeah. Just from the basic transformer definition, right? I will not go through it over again. Just from the basic definition. Now, obviously, in a potential transformer, what you do? We just step down the voltage. Okay, to our measured voltage, and we measure. So if n1 is 1000, we step it down by 1000 times. So if the voltage is 110 kilovolts, if I step it down by 1000 times, it will be 100 and what will be the secondary? AC secondary will be 110 volts. So I can easily measure 110 volts, but 110 kilovolts, measuring 110 kilovolts will be very difficult for directly for a measuring instrument, right? I can step it down and then measure. So like these are few key points for potential transformer, also known as parallel transformer. Secondary instrument for the measurement will be voltmeter, pressure coil of the voltmeter, or pressure coil of the energy meter. Anything can be as a secondary instrument for measurement. And like I explained this as a starting as well, your N1 will always be more than N2 because I'm stepping down the voltage, and as the voltage reduces, turns will also reduce. But for current, it is inversely proportional. That is what is present in the current transformer. So here we use a step up transformer. Here we use a step down transformer. Here we use a step up, not step down current transformer, but we use a step up because generally we talk in terms of voltage. So we use a step up transformer. So in step up transformer, what do we do? So basically in step up transformer, what we do is the current is reduced. So here, what is the amount of current that is flowing? The amount of current that is flowing, let's assume it has 1 kilo amperes. And if the turns ratio or something like this has lower number of turns, let's assume this has only single turn and this has 1000 turns. Okay, so the current will simply get divided by 1000 times because this has more turns. The current will be inversely proportional to the turns, so it will be divided by 1000 times. So out I2 will be equals to, all this is in RMS, I'm talking about RMS only. Okay, so I2 will be equals to 1 amperes. So 1 amperes I can easily measure, right? But 1 kiloampere, measuring 1 kiloampere will be very, very difficult task. So obviously from this relationship I can observe that N2 will be greater than N1. N2 will be greater than N1. That is what I observe in the relationship, right? So these are few key points about the current transformer known as series transformer. Secondary instrument for measurement is ammeter, current coil, or wattmeter, or current coil of wattmeter, or current coil of energy meter. The primary winding of the CT usually consists of a single turn or a bar. It only consists of a single turn, and this design minimizes the amount of conductor material required by replacing the number of turns, making it cost efficient. So this, if you use bar, right, it reduces the cost. Basically, that's not that important for gate point of view. Just few theoretical points. These are few ratings about the CT ratings, and all those things are given. Okay, so one thing that you should know is when CT primary is energized, the secondary winding must never be left open. Why it should never be left open? The secondary, if the secondary winding is left open, then that means the I2 current is 0. If the I2 current is 0, then what happens is the flux produced by the secondary is 0. Phi 2 is 0, right? Phi 2 is 0. If phi 2 is 0, that means there is no opposing flux. If you remember, what would have happened in a transformer is some current is there in the primary, due to that some flux is produced, so flux flows. Then due to this flux, a current gets generated, and this current in turn generates a flux which opposes the initial flux. Lenz's law. Please, if you couldn't understand this, we have to go and study electrostatics and magnetostatics from me. Go back and there. So Lenz's law will be there, that will oppose this initial flux, right? Yeah, now if this I2 is 0, that means there is no flux, like there can't be any secondary flux, right? If there is no opposing flux, there will be huge flux flowing in the whole transformer. That can damage the transformer, okay? That can damage the transformer. So, hence, phi core will be very high. If phi core is very high, that can actually damage the transformer. Okay, it can actually damage the transformer. So that is one thing that you should know, that you should keep in mind. Okay, so that is one thing. Now that's why we never keep the secondary of a CT, current transformer, open. You can keep the secondary of a voltage transformer open, but never keep the secondary of a current transformer open. Okay, that can damage the transformer. Okay, so now we'll basically come to the errors and the equivalent phasor diagram. So this is the equivalent circuit of a transformer, right? If you know, there is a secondary winding resistance, secondary winding reactance. This is the secondary, this is the primary. Okay, this components, I hope you remember, this is the like magnetizing component, okay, of the transformer, and this is the core loss component of the transformer, right? That is parallel. Eddy current. Also we talk about the eddy current that is flowing on the core, correct? And this is the primary, and this is the actual IP dash, actual primary that is flowing in the coil of the transformer, and this is IS. Okay, so there are a few errors here. What are those errors? I will talk about that. So phi m is the working flux of the transformer, N is the turns ratio, N is upon NP, I0 is the no load current, I mu is the magnetizing current, IW is the core loss component, right? And what is delta? Delta, right? Delta is the angle between ES and IS. So there is ES and IS here. So it will be the angle between this ES and IS, because there is some reactive components present on the secondary. So let's start with the phasor diagram of our current transformer, right? So I have a working flux phi, okay, that will be generated due to the voltage Vp, and due to this phi, a induced voltage will be generated, that is EP. Okay, that this is the induced voltage. These two voltages are induced actually, and I will not explain this diagram fully, because this you already study in machines, so I will not go too much in depth here. Okay, induced voltage. So this is the induced voltage, correct? So what I can say is that I have a phi. So in parallel to this phi, I will have the magnetizing component current, I mu, right? Magnetizing component current. Due to this only the phi has been generated. Now in perpendicular to this phi, I will have the core loss component, because the magnetizing component and the core loss are perpendicular to each other, and the summation of these two will give me I0. Okay. And one thing I know is the angle between, like, due to this EP, right? This EP, a secondary voltage will be induced as well due to mutual inductance ES, and the angle between ES and IS is delta. I have already mentioned it. Angle between ES and IS is delta, secondary. So if what will be IP dash? This is IP dash actually. What will be my IP dash? IP dash will just be equals to N times IS. The magnitude will be N times IS only, but in opposite direction. It will oppose, because these currents will be in opposite direction. Both of them will oppose each other, as the secondary flux is opposing the primary. I will not go too much in depth in the phasor diagram now, because this has been taught you in machines. So I'm not going into much. So that's why this will be opposite. So the sum of IP dash and I0 will give you IP. Now there is a problem here. This is the turns here, number of turns of the transformer, right? But what I was expecting this ratio, IP dash upon IS. Not IP dash, sorry, IP upon IS. I was expecting this ratio, but currently the transformer ratio N is IP dash upon IS. So there is some error. So that is the error that we need to identify, right? So like this alpha angles between I0 and phi m, also known as hysteresis advance angle sometimes. Okay, so the error is what? I was expecting my transformation ratio N to be simply IP by IS, right? But what is this? N is equals to what? IP dash by S. So what is my actual transformation ratio? A. A will be total IP upon IS, correct? So what is IP? IP is sum of these two, I0 plus NIS, correct? So that is what is written over, I0 plus NIS divided by the IS. Obviously IS will not change. So this is the transformation ratio that I am actually getting, but I was expecting this transformation ratio. There is some error. The error is ideal N minus A divided by the actual. Okay, so N minus A divided by the A. This is known as the ratio error of the transformer. So don't worry, they will define all these things, error and all these things. They will define just few things you need to know. So I need to find out this ratio error. How will I find it out? So actually, I have to find out, like, what I have to do is I have to find out IP. What will be exactly IP equals to? So IP, from the phasor diagram, if I want to write the magnitude of IP, right? I'm just interested in the magnitude of IP because my ratio will be magnitude of IP divided by magnitude of IS. This phasor, these are all phasor quantities, right? Okay, so what is the magnitude of IP? The magnitude of IP will be like, I have two components. One is this, another one is this. Okay, I naught. So what is the angle between? I can use a parallelogram law, right? I can use parallelogram law of vector addition. Parallelogram law of vector addition. Okay. So what is the angle between these I naught and IP dash? It is, this overall is 90. This is delta, this is theta, this is alpha. So what will this? This will be 90 minus delta plus alpha, right? Okay, not exactly. Yeah, this angle will be 90 minus delta plus alpha plus theta. So what will be the angle between these two? It will be theta plus this, 90 minus delta plus alpha plus theta. So theta will get cancelled. It will be only 90 minus delta plus alpha. So if you remember the formula, this is supposed to be a square NIS whole square plus b square. B square is I naught whole square plus 2 cos of 2AB, that is NIS into I naught into cos of angle between the two. What is the cos of angle between the two? It is 90 minus delta plus alpha. Correct. So this will be further simplified into NIS whole square plus I naught whole square plus 2n IS I naught into sine of delta plus alpha. Now what we do is we make few assumptions. What type of assumptions? I write this I naught, right? I write this I naught, as this I naught is anyways very small compared to this NIS. I will write this I naught equals to I naught sine delta, for my convenience, sine delta plus alpha. Okay, for my own convenience I will do this. I will replace this I naught with this. Why? Because then I can use this as a formula of a plus b whole square. Okay, because this, right, if I change this will not affect the overall result. Why? Because my NIS will be very higher than I naught. Okay, it will be very higher than I naught, so it doesn't matter because I know, right? So what is the primary current? Like, what is this no load current, right? No load comparative current will be very low compared to this NIS, right? Because IP dash will be higher, else error will be huge. So obviously I can do this approximation just to simplify the equation. So this will become a plus b whole square NIS plus I naught whole square, not NIS plus I naught sine delta plus alpha whole square. If I take the under root, it will simply become NIS plus I naught sine alpha plus delta. So if I find out the ratio, the actual transformation ratio, what was it? It was IP by IS. So if I take this IS in the bottom, right, it will become N plus I naught IS plus sine alpha plus delta. So this is the extra term that I'm observing that was not supposed to come. Okay, this is the error basically. So this is the error, and there is another term known as the tan of angle. So what we do, we actually used to find the tan theta. Okay, theta is the angle between this IP dash and IS. Okay, now what we assume, like we just assume to simplify the calculation, that's it. Assumption is the component of I naught is mainly dominated by the magnetizing component because the core loss component will be very low, and the component of this top I side, right, will be mainly dominated by IP dash. So my assumption is this IP dash is almost perpendicular to I mu, right? So theta, the angle between the NIS and IP, tan of this angle will simply be equals to what? This will simply be equals to I mu I mu by NIS. Altitude upon hypotenuse, right? No, not hypotenuse, sorry, altitude upon base. Okay. So I mu upon NIS. So this will be equals to I mu upon NIS. So from here, like this is just an approximation. My assumption is I mu is anyways very lower, so we can directly equate this with respect to theta as well. Okay, in the next like slide I have explained that only tan theta will, as theta is very low, this can be directly be equated with I mu upon NIS. But to remember, this has to be in radians. We have to convert this into, like this is in radians. This is in radians, and if I want to write in degrees, I have to multiply 180 by pi. So that's the only thing that you need to take care. These are the few formulas that you need to understand. Okay, the current ratio error and the tan theta. These two formulas that you need to remember for ESC, mainly for ESC. GATE also this is required, but they will mainly ask conceptual questions mostly. I hope. So now ratio error I explained previously as well. Here also, if you see that extra term, right, that was coming. Ratio error is basically the difference of nominal error. The error, like the ratio that I am supposed to get, that is n, minus the actual ratio r divided by r. Okay, so the actual ratio is this, right? This value, n plus I naught upon is. Okay, so I hope you understand the ratio error concept as well. Now we will solve few questions. So first I will show you all the questions, and then I will solve all the questions. Right? You can take a pause the video and take a screenshot of all the questions. Then this question, this question, this question, this one, and I think this one is this is there, and this is the last question, I think. Yeah, this is the last question. You can pause the video and try all the questions by yourself, and then I will solve all the questions. Okay, so let's start with this first question. So we have a 500 ampere to 5 ampere 50 hertz current transformer, has a single turn primary. So its NP, right, is single. Okay, and it is 500 to 5 ampere. So the ratio of NP by NS will be what? Unless and until specified, we will not consider any errors. Unless and until specified. So I know my primary by IS, this is a current transformer. It is 500 by 5. This will be equals to my NP by NS. So my NS will simply be equals to 100. Okay. So the secondary burden consists of a pure resistance 1 ohm, and it draws a current of 5 amperes. So I have a secondary burden RL which is of 1 ohms, and it draws a I2 current or IS current is 5 amperes. The magnetization of the CT core requires 250 ampere turns. What is the ratio error? So the magnetization of the core, right, requires 250 CT. So the turns ampere turns, right? Ampere turns of the core. Ampere turns of the core is what? This will be equals to 250 ampere turns. Now this like this, I can equate this with respect to the secondary and with respect to the primary. So with respect to the secondary, if I equate this, what will I get? Okay, so with respect to the secondary, this is the ampere turns, 250 ampere turns. So what is the current basically? What is the secondary current? Okay, or the magnetizing component of current. What will be the magnetizing component of current? Magnetizing component of current will be ampere turns divided by the number of turns. Okay, so I can, like, this will always be same. So if I divide it by turns on the primary end, on the primary side, if I divide by the number of turns, what will be it? Ampere turns is 250 divided by the number of turns in the primary. I have only one number of turn, right? In the primary I have only one number of turns, so it is one only, so it will be 250 amperes. Now my primary current was supposed to be NIS, but actually I have this magnetizing component current, right, as well. So it will be plus IM. Now remember that this will be totally perpendicular to the actual secondary component. They will be almost perpendicular. That is my assumption. So IP will just be no angles, nothing has been given, so I'll assume these two to be perpendicular. So that is my assumption. These two will be perpendicular. So I can simply do the A square plus B square, as both of the components are perpendicular to each other. So what will be the IP current? IP current is actually equals to N times IS. That is, N times IS is this 500 plus this 250 whole square. So 500 whole square plus 250 whole square. So it will be 250 250 under root 5. Okay, amperes, 250 under root 5 amperes. But my n was supposed to be this, right? And turns ratio was supposed to be 100 actually. But now what is the turns ratio? Actual turns ratio. It is IP actual divided by IS. This is IP dash actually. This is IP dash. Okay. So I'm observing that I'm getting a current of 250 under root 5 divided by IS. Secondary current is 5 amperes only. Okay, I've already taken a magnetizing current on one. I will not take on both ends, right? So like this, how do you find out? This is the magnetomotive force, right? This is basically NP into IM. Okay, or what we do is NP into IM. Okay, or like for the primary end and for the secondary end also you can compute with the same thing, because number of turns in the primary is single, so it becomes very easy and equivalent, easy to solve for us, right? So this becomes 50 under root 5, but my nominal ratio was supposed to be 100. So what will be my percentage ratio error? Although this is a very old question, nowadays they will give you exactly what the definition of ratio error. Okay, don't worry about that, as this was an old question, and in books generally we write the ratio error like this. It is nominal ratio minus the actual ratio divided by the actual ratio into 100. Okay, so your ratio error will be 100 minus 50 under root 5 divided by 50 under root 5 into 100. So this will be 50 into 5 under root plus 100 divided by 50 into 5 under root into 100. It will be minus 10%. So this much amount of error you will get, minus 10.55%. So this much amount of error you will get. Now I understand that you will not be able to solve this question first time if you haven't studied machines. So that's why I highly recommend you go and study machines. What does this MMF means? This is actually the magnetomotive force, MMF, of the transformer. If you don't study transformer, you will not be able to solve this. So it's good if you know the transformer, right? So my assumption is NIS and IM will almost be perpendicular to each other. So that is my assumption. Assumption is NIS will be somewhere around here and IM will be somewhere around here. So from here only I will be able to calculate my IP. Okay, so they are almost perpendicular to each other. So that's how we solve this. So that's why I use the Pythagoras theorem basically. Okay, let's solve the second question. So here a 50 Hz current transformer with a bar primary has a secondary winding of 500 turns. Bar primary means single turn. Bar primary means single turn. Okay, so that is what bar primary means basically. Okay, so now what we have, and has a secondary of 500 turns. The secondary supplies a current of 5 ampere into a purely resistive burden of 1 ampere. The magnetizing ampere turn is 200. What is the phase angle between the primary and the secondary currents? Okay, what is the phase angle between the primary and the secondary currents? So how will I identify the phase angle between the primary and secondary currents? So again, my assumption is nothing is mentioned. So first thing what I will assume is my NIS will be here. IS is somewhere here. This is my IM. This is my IO. IP. Okay. So I can directly say that like it's the same question only, just that they have asked the phase angle. So you have to find out the phase angle as well. So I have to find out this angle, gamma. Okay, how will I find out? I will show you. Okay, so they have given me that the secondary supplies a current of 5 amperes and winding turn is 200. So what will be this IP dash? What will be NIS? NIS will be this turns ratio, that is 500 into 5 amperes. That is 500 into 5. Okay, now what is IM? IM I need to find out. IM will be what? It will be NP into IM. Magnetomotive force they have given me as 200 sorry, not, yeah, 200 ampere turns, right? This is equals to 200. And I know NP is 1, it's a singleton coil, so IM will simply be 200. Okay, so from here I can directly calculate my magnitude of IP. Magnitude of IP will be what? It will be N into IS whole square plus IM whole square. Okay, so this will be equals to what? This will be N into IS. N into IS is 2500. What I can do is I can take 100 common, right? So what we can do is this 100 will be outside. This will be 500 into 5 whole square. 25, so 625 into 200, 629 under root 629. Okay, this will be basically the result. Okay, so this is the magnitude of IP. Now what is the angle between the currents, right? Secondary currents. So what is this angle? This angle is 90. I just need to find out this angle. What is this angle? Let's name this angle as anything like theta x or something. So theta x will be how much? It will be tan inverse of altitude upon base. So altitude is how much? It is 2500. What is the base? Base is 200, correct? So if I just calculate this tan inverse, right, 25 divided by 2, tan inverse of this will be almost 85. Nothing is mentioned, so this will be my assessment. This will be my starting point always. Okay, 85.426 degrees. Now what is gamma? The angle between the current, right? Angle between the primary and the secondary current, IP and IS. It will be 90 plus gamma, basically. Not gamma, sorry, 90 plus theta x. That is gamma basically. This is equals to what? 90 plus this. If I add 90 with this, this will be 175.426 degrees. Okay, so in radians, if they want to ask in radians, how do you write in radians? You will multiply this by 180. This gamma can be 175.426 degrees, or if I want to convert this into radians, it will be 175.426 into pi divided by 180. Okay, this also I can do, right? So in radians, if I want to calculate, into pi divided by 180, this will be 3.06 radians. Now many students, what they do mistake, they actually find out this, right, and they write the angle as this, or they just find out theta x, they just find out the theta x, right? Yeah, that is what I am telling. They just find out this angle and they directly write this, which will be very, very wrong. Okay, you cannot do it. Okay, so what is the next question? Find the core flux in the CT of the previous problem under the operating condition. How do you find out the core flux? So core flux, right, if you remember, there was one formula. Okay, this is like machines chapter. What was the formula? Core flux ES will be simply equals to root 2 pi f phi m, and there was a fifth term, root 2 pi f phi m. There were few, like okay, f is there, and turns, number of turns, right, ns, correct? If you remember, recall this correctly, this was the formula. If you know from machines, you will remember this, right? So this ES is what? ES is the secondary voltage. ES equals to IS into RS, right? That's it. IS is 5 amperes and RS is 1 ohms. So it will be simply 5 volts. Root 2 into pi into F. F is 50 basically, because they have mentioned it as 50 hertz, and phi m we need to find out. And NS is what? NS is basically the secondary turns. Secondary turns, how many secondary turns we have? It's 500. Correct. So from here you will be able to solve the second part. That is the secondary part. This is the machines concept. This is not measurement concept. Okay. So, but this is linked. This question is linked between machines and measurement. This is a very, very good question. So my phi m will simply be IS into RS. IS into RS is 5 simply, divided by root 2 into pi into 50 into 500. Okay, inverse into 5. So it will be all this mess. This will be equals to 45 micro Weber. This will be the unit of flux, right? 45 micro Weber. Okay, so I hope you understood like this question. This is a mixed question between machines and your measurements. Okay, so let's solve the next question. And in the next question, I will exactly explain what is this phase angle error, right? So here, actually, I will just make a few like changes in my explanation. So what I will do is, I will copy this thing. I have made a bit of mistake because this tan theta, right, is not simply equals to this. This has a better explanation. So I was thinking the same. So here, right, I have the current I mu here, correct? And I have this NIS here, right? NIS. That is with a delta angle with respect to this IW, correct? The core loss component. So that has an angle of delta. Okay. And I have this component of current, that is IP. And the angle between these is theta. And I want to measure this angle theta. How will I measure? So what I can do is, I can break this NIS in two components along this IW and I mu. So this, right, this can be broken in two components. This equivalently we can write one horizontal component. Horizontal component is IW plus NIS into cos of delta, and the vertical component is I mu plus NIS into sine of delta, and this is IP basically. Okay, what is this angle? This angle is delta plus theta. This angle is delta plus theta. Delta plus theta. Now can you write delta plus theta? What will be delta plus theta? Delta plus theta will be tan inverse vertical upon horizontal. So what is vertical? Altitude is this IW, not this. Yeah, this is only IW plus NIS cos delta. So this will be your okay. Am I correct? Oh, no. This is the horizontal, right? This is the altitude. So it will be I mu plus NIS sine delta divided by IW plus NIS cos delta. Okay, so I already know delta. Delta will be given, right? I already know delta, so I can write my theta. So this right, this can have better explanation actually. My theta, in precisely theta will be delta. Sorry, this value, that is tan inverse. Like I can write this properly. It will be, this is denoted as what? This is known as the phase angle error. Okay, phase angle error. This will be tan inverse the numerator, that is I mu plus NIS sine delta divided by IW core loss component plus NIS into cos delta. Okay, minus delta obviously will be here. So this will be the actual result of the phase angle error. This is known as the phase angle error. Okay, and if you want to convert this into radians or degrees, you can simply convert it, right, according to the conversion. But I was like I also couldn't understand this first time, and I studied from many educators, but I was not able to understand. But now finally I'm able to figure out. And please do hit the like button if you are able to understand this concept, right? This is a very, very important concept, and many educators, they like write thousands of, like not thousands, tens of pages to prove this, and they just waste time. But it is very important to understand. I also at the first time couldn't understand this particular point. That's why I wasn't able to explain that. But now I am able to understand what is exactly the phase angle error. Okay. Like, why is this called phase angle error? Because my angle was supposed to be here, right? It was almost equals to NIS. My IP was supposed to be equals to NIS. So it was in the same phase as NIS, but it isn't, because there is a other components, right? That's why IP has been shifted by theta angle. So that's why there is a angle error of theta. So to identify theta, you simply break this NIS in two components, right? And then you totally calculate delta plus theta, and from there you derive this. Okay. So I hope you understood. Now we'll solve a question on this, and you will totally get the understanding of this. So this is the question. So current transformer has a two primary turns. So NP is 2, NS is 200. The secondary winding carries a current of 5 amperes. IS is 5 amperes. And has an impedance of 0.75 plus J 0.3 ohms. So its ZS is 0.75 plus J 0.3 ohms. So from here, can I find out the delta? Yes, this is the secondary winding impedance, right? Secondary impedance. So this is this angle of the impedance will give me the angle between the secondary current and voltage, and that is equals to what? That is equal to delta. So simply doing the tan inverse of this, I will be able to find out the values. So if I take the tan inverse, it will be 0.3 divided by 0.75. Tan inverse of this will be 21 point, like this is tan inverse 0.3 divided by 0.75. Okay, so delta will be, if I do the tan inverse, delta will simply be equals to 21.8 degrees. Okay, this will be my delta value. Now, can I simply identify delta plus theta? This I have already derived, right? This I have already derived in the previous slide. So I'm just directly adding the values. So what will be delta plus theta? So delta plus theta will be I mu plus NIS sine delta. So what is I mu? So this time I will not use that approximation. Like previously I derived the formula using approximation, right? Here as well. If you see, IM and NIS were almost perpendicular. I was doing the approximation because they haven't mentioned any other component. They haven't mentioned core loss component. Nothing has been mentioned. So we'll approximate. I will assume core loss component to be almost zero, negligible. Only magnetizing current is present. I will neglect it. Okay, and I will assume I have a purely resistive load. Purely I had a resistive load, so hence there was no delta. Delta was zero. But now this is not a purely resistive load anymore. There is a secondary impedance. Okay, so if there is secondary impedance, so now there will be some delta and there will be some core loss component which is comparable, because my magnetizing current is 10 amperes and my core loss is 8 amperes. Both are comparable. Both are not negligible. So my I mu is 10 amperes. And my IM is 8 amperes. Okay, so they are comparable. I cannot neglect. So this is the exact formula. Do you need to remember? No, you no need to remember. Just use the phasor diagram. Okay, no need to remember. Okay, and if you did enjoy this concept, and if you finally got a concept that you don't need to remember this, mug up this formula, please do hit the like button and comment down below that you are really enjoying this, because I hope you understand the level of that level that we need to go in depth to understand this and then explain as well. So I hope please do hit the like button, and this much we expect at least, so that actually satisfies us that you are understanding the concepts. Okay, so this will be delta plus theta will be equals to tan inverse some value I mu is 10. First of all I will calculate this, right? First of all I will calculate this, that is NIS. N is 5. Not 5, sorry, N is 200 and IS is 5 into sine of delta. Delta is 21.8. Sine of delta will be simply 371 plus 10. So it will be 381.37. divided by IW. IW is this is NIS. NIS is 5 into 200 into cos of delta 21.8, cos of 21.8. It will be 928 plus 8. It will be 936.48. And if I take the ratio of this is this 2 3 7 and then take the tan inverse, this will be 22.18 degrees delta plus theta. But I need to find out theta, right? Theta will be this 22.18 minus 21.8, almost equals to 0.389 degrees. Okay, so you can observe this is a very, very small value, and if you compute in radians, it will be even smaller. Okay, so yeah, the ratio error will be very, very small, but I hope you understood this point, right? Okay, one point I went wrong here. It was NIS, right? And N is basically not 200. N is 200 upon 2. That is 100 actually. That is my mistake. So I made a mistake over here. This should be 100. Okay, so this should not be same. Made a mistake. So if I multiply 100 into what is the current, that is 5, right? 5 into 21.8 sine, this will be 185 plus 10 also is there, so 195.6 68 divided by 500. N is 100 and IS is 5 into cos delta, cos of 21.8 plus the core loss component current, that is 8, right? That is 8. So it will be 472.24. So it is 195.68. Now if I take the tan inverse of this, it will be 22.5. So I was wrong here. It should be 22.8. Okay, 22.5. So now if I subtract from delta, what will I get? Minus 21.8. It will be almost 0.7 degrees. So your answer will be almost 0.7 degrees. This will be answer. Okay, I hope you understood. Like, don't make this mistake, right? We don't put simply here 200. Don't put 200. That is what why I am marking out, because if you put here 200, your answer will be wrong. Okay, you'll go wrong. So just be careful about putting the values. Simply don't put 200 here, because this is not NS, this is N. Basically the ratio, transformation ratio, right? If the secondary has current as 5 amperes, what will be the primary current? It will be very, very higher, but you have to take care of the transformation ratio. Okay, so I hope you understood this concept. This is a very, very good concept, and if you did enjoy this question, please do hit like and comment on the video below. Okay, so let's do this next question. We have a current transformer with a rating of 300 to 5, right? Has a magnetizing current of 12 ampere and the loss component of the exciting current is 9 ampere. So I mu is 12 ampere and IW is 9 amperes. Okay, so what will be the phase angle between the induced EMF in the secondary, that is ES, and the current? Okay, if the phase angle between the induced EMF and the current, angle between the induced EMF and current IS is equal to 30 degrees, that is equals to what? That is equals to my delta, correct? What is the phase angle error at the rated current? Rated current meaning at the this secondary rate is known as the rated current. If it is given like this means I am operating at 5 amperes. 5 amperes is the rated current. Okay, that's why CTs are generally represented like this only. So here my IS secondary rated current will be simply 5 amperes. Again, I will use the same like phase angle error formula only. So again, my theta plus delta, you can always draw the phasor diagram if you tend to forget the formula. Okay, you can always do it, but I have in my brain, or I can just take it from here only. Take these two things from here only. You can draw the phasor diagram if you tend to forget in the examination hall itself. This will be equals to tan inverse I mu plus NIS sine of delta divided by IW plus NIS into cos of delta. So now I will just put the values. I mu, I know delta, I know. NIS will be what? NIS will just be the rated primary current. Rated primary current is 300 amperes. Okay, so we'll just put all the values here. So 300 into sine of 30, right? It is basically sine 30 is 0.5 only, plus I mu is 12, so it will be 152 tan inverse 152 divided by, this will be again 300 into cos of 30 this time plus IW, this will be 268.8. Now if I take the tan inverse of this will come out to be 29.486. okay, so angle comes out to 29.486. now if I find out the like difference, okay, phase angle error, am I doing this correctly? This is 9 only, yeah, this is 300. Yeah, I'm operating in rated condition. Okay, again I made a mistake. No, did I make a mistake? No, NIS is this only, rated primary current, right? Yeah, 5 into 60, yeah, this is correct. Everything is correct here only. So my angle, right, angle difference will be what? Theta is 30, so subtract by 30, delta is 30, so it will be delta will simply minus 0.51 degrees. So this will be the, not delta, sorry, this will be the theta, this will be the phase angle error, it will be minus 0.51 degrees. okay, so I hope you understood the what is the error. Error is, it is phase angle is actually negative, so it will be somewhere around here. My IP current will be somewhere around here. Okay, it will not be here, it will be somewhere around here. Okay, so yeah, I hope you understood this particular thing. IP is cos delta. Yeah, so now let's solve few more questions. This is another question. A 50 hertz primary current has a winding turn of 100 and 5 ampere delivering to a purely inductive load with impedance of 1.5. so secondary current, right, IS is 5 ampere, but it is delivering to a purely inductive load. And what happens to a purely inductive load? It totally lags the voltage by 90 degrees. So if my ES, induced voltage is here, this is my 5M, correct? So my induced current in the secondary will be something like this. It will totally lag, right? IS will be here, 90 degrees. And the magnetizing current is here only, IM. But they are asking me what is the phase angle between the primary and the secondary current. So what will be the primary current? NIS will be again, NIS will be on this region only, NIS will be here only. Okay, J times IXL. Sorry, my voltage actually in case of purely inductive load, right? So the voltage actually totally lags from, remember the voltage totally lags because voltage is equals to V equals to JIXL, correct? JISXL. So sorry, my voltage actually will okay, this is plus 90. No, it is correct. Current will lag 90. No, it is correct. Yeah, current will lag. So my IS will be here again. NIS will be here, right? NIS will be here. And what about my I0? They have provided the magnetizing component of current is 125 and with an impedance of 1.5 5 ampere 100 turns. Okay, so what will be the angle between the primary current? This is the primary current, right? This is the IP primary current, and the secondary current, it is totally 180 degrees. So there is a total 180 degree phase shift between the primary and the secondary current, right? So angle between IP and IS is 180 degrees. Okay, so this will be like pretty straightforward. You don't need to do just phasor diagram concept, you should know. So this is more of like a what do you say, like a transformer question, machine question, not like a measurements question. Now let's read this. Which of the following factors does not contribute to ratio and phase angle errors? So just a bit of theoretical knowledge you should have for ESC purpose. Impedance of the secondary winding. If impedance changes, right, there will be phase angle error because it is a function of delta. my phase angle, right? Theta is a function of delta. Okay. So delta is function of secondary. It is secondary. It is function of secondary coil, right? That's why. Variations is in primary winding current. If there is a variation in primary winding current, obviously NIS will vary, right? NIS will vary as theta is a function of NIS as well. So frequency changes in the primary winding. Now, if frequency changes, I know my phi m is a function of frequency, right? And in turn, my Im is a function of phi m. Correct? So obviously, if phi m changes, Im will change, and phi m in turn is function of frequency. So obviously, this also will be affected, and ratio error also the same only. Now, power factor of the primary winding. Does it depend on the power factor of the primary winding? No, because I compare with the refer current from the secondary. I compare with the IP dash. Okay, not with IP. So actually, it does not, the phase angle error does not depend on the power factor of the primary winding. So option A will be correct. Okay, these are few theoretical questions that we should know. This is another GATE question that the GATE gave. Okay, on 2024. So we have to match the following, right? After many years, they gave a match the following option. So we have a current transformer and potential transformer. Now, current transformer primary is connected to parallel to the gate. No, if current transformer is connected to parallel, no. Current transformer is connected in series. Current transformer open circuited, secondary is not desirable. We'll do this later on. Primary current is the line current. Yes, for a current transformer, primary current will be the line current. It will be the main current of the load, right? Kiloamps in kiloamps. So first match I can get X is R. Potential transformer, primary is connected to parallel to the grid. So Y will be P. Now there are two more. Let's read this. Secondary burden affects the primary current. And open circuited secondary is not desirable. This, why I mentioned this today's lecture. Open circuit is not desirable for current transformer. Why? If open circuit is not desirable for current transformer, because my flux phi 2 will be 0. Hence there will be no oppositions. Hence my core flux phi m will be very, very high, as phi m is equals to phi 1 minus phi 2 primary minus secondary flux. And as it is gone, so it will be very, very high. Core can get damaged. Huge flux there is. Core can get there will be saturation of the core and core can get damaged. There will be huge heat, eddy current losses. So I don't want that. That's why I don't open circuit the secondary. What about the secondary burden affects the primary current? Now for current transformer, right? The current is fixed. I primary is fixed. For potential transformer, but the VP is fixed. If the VP is fixed, that means my VS is fixed, because they are related with a ratio. So VS is fixed. Is my IS fixed? No. IS actually depends on the impedance. IS is VP VS divided by ZS, right? So obviously, if the burden, that is the secondary load, changes, my IS will also change. Exactly, that is written, right? Secondary burden affects the primary current. So IS in turn is related with the primary current, because IP by IS is related with the turns ratio. So obviously, option this will be point to S, right? Because they are related. So option X points to R and Q, X points to R and Q, Y points to P and S. Option C will be correct. This is a very, very good question. A lot of concepts will be just cleared by reading this theoretical points. So this can be asked in ESE. Okay. Now let's do this next question. A current transformer with a current rating of 200 to 5 has a magnetizing component of 2.5 amperes. It has a magnetizing component of 2.5 amperes. So my IM is 2.5 amperes and the rated primary current, right, IP is 200 amperes. Okay, or we call it IP dash. If the secondary winding is purely resistive and the transformation ratio at rated current is 40 if the secondary winding is purely resistive, okay, and the transformation ratio at rated current is 40, what is the loss component of the exciting current? Okay, this is actually, this should not be amperes, this is just transformation ratio, right? So this will be 40.4 only. This should not be amperes. Transformation ratio doesn't have any units. What is the loss component of the exciting current? So what they have told me, the transformation ratio, right, is, it should actually be, ideally it should be what? It should be N, right? Ideally my transformation ratio was supposed to be n, which is supposed to equals to 200 divided by 5, which is 40 basically, but it is not, it is 40.5. This is the actual transformation ratio, and if you remember, we derived a formula for actual transformation ratio. I can simply use the okay, not this, I can use a phasor diagram as well, right? I can use a phasor diagram. So from here, what I can say is that I can talk about a ratio. What is the ratio? R is equals to IP, actual transformation ratio, divided by IS. And this I derive, the magnitude of IP was equals to NIS plus I naught sine delta plus alpha. If you remember, it was sine delta plus alpha. So I just derived this in today's lecture only. NIS into I naught sine delta plus alpha. You know what is alpha and delta, all these things you know already. Okay, so my transformation ratio, right, R, this is N plus I naught upon IS. I naught upon IS, I don't know. I know IS, but I don't know I naught. What is delta upon alpha? So delta, they have told me that it is a purely received load. If it is a purely received load, my delta will be simply 0 degrees, no angle. And what about the alpha? Alpha I don't know. Okay, alpha also I don't know. Alpha I need to find out. It is angle between loss component and current component, but I know IM, right? I know magnetizing component. IM is 2.5. So what is IM equals to? IM is equals to actually I naught cos of alpha, because this was the angle, right? Alpha was the angle between the I naught and the magnetizing component. It was I naught cos alpha. If you remember, that is how we defined the alpha, right? If I go back here in the phasor diagram, yeah, that is how we defined alpha. So here this will be equals to they have given me actual transformation ratio 40.4, and ideally it should be 40 plus I naught sine of alpha, basically I naught sine of alpha. This is what actually, this is the loss component, this is the loss component of the exciting current. Why? Because this is the magnetizing component and the loss component is simply I naught, IW will be I naught sine alpha, the perpendicular component, basically this component, right? Perpendicular component. So divided by IS, I know IS is how much? IS is basically the rated current in the secondary side, right? It is 5 amperes. 5 amperes. So from here I can directly find out the loss component, IW. IW will be equals to 40.4 minus 40 into 5. So it will be simply equals to 2 amperes of current. Okay, so loss component will be 2 amperes. This will be your answer. So I've tried to explain the topic in the most simplest and least difficult manner, because I know there are many formulas that you need to remember, and in CT just the current transformer PT, two things you need to remember. One is the ratio error, another one is the angle error. How to find out the angle, I have told in the most lucid manner. You will not find it anywhere else. And the how to find the ratio error also I have told you, like just derive in front of you, right? So you can always derive if you want, or you can directly solve. Okay, and ratio error definition is this. Don't worry, they will mention, generally they will mention in the nowadays they will mention in the question itself what they are talking about by ratio error. What do they mean by ratio error? Okay, they will mention this. So most important factor is these two, this page, right? This page is the most important one, this phase angle error and the ratio error. These are the two things. So I hope you enjoy this CT and PT, and yeah, that's it basically for this whole sequence of chapters, and I hope to see you in the next video. Until then, happy learning.